The Theory of Evolution. In 1859, Charles Darwin published On the Origin of Species, introducing evolution by natural selection. The theory proposed that organisms with advantageous traits survive at higher rates, passing those traits forward. Over extended timescales, accumulated changes produce new species through differential survival rather than directed design. This proposal challenged prevailing assumptions about the fixedness of biological forms. For centuries prior, life was considered unchanging and purposefully designed. Darwin's mechanism suggested otherwise, that current forms emerged through iterative adaptation over deep time, not through predetermined intention. The reaction was immediate and divisive. Religious institutions rejected the framework outright. Some scientific communities questioned whether selection pressure alone could account for observed biological complexity. Despite extensive fossil evidence, genetic confirmation, and direct observation of speciation events, evolution remains contested in certain populations. Creationist frameworks and intelligent design proposals continue to hold influence in specific cultural contexts. Evolution has become foundational to modern biology, informing genetics, medicine, epidemiology, and computational modeling. However, philosophical implications persist. If human forms are products of iterative environmental pressure and random mutation, questions arise regarding significance, teleology, and the existence of intrinsic purpose. Evolutionary processes continue in contemporary populations. Human biology, cognition, and behavior remain subject to selective pressures. Whether evolution follows a directional trajectory or represents undirected drift through possibility space remains contested. Some interpretations suggest liberation in purposeless emergence. Others find the absence of predetermined meaning problematic. The implications extend beyond historical explanation. Evolution functions as a lens through which existence itself is interpreted, a reminder that change is constant, that adaptation determines continuation, and that permanence, even of species, is illusory. Whether this framework diminishes meaning or generates alternative forms of significance remains unresolved. What remains clear is that organisms are shaped by forces predating memory time, contingency, and environmental constraint. Whether understanding this diminishes human centrality or establishes appropriate humility is a question each observer must evaluate independently. The debate over evolutionary mechanisms continues across multiple scientific and philosophical domains, with new evidence regularly introduced but fundamental questions about directionality, purpose, and ultimate meaning remaining persistently open. Heliocentrism. For extended historical periods, Earth was considered the center of cosmic structure. The sun, moon, and stars were believed to revolve around terrestrial observers in divinely ordered patterns. This geocentric model was not merely astronomical, it confirmed anthropocentric significance and positioned humanity as creation's focal point. In the 16th century, Nicolaus Copernicus proposed a heliocentric model. Earth was not stationary but orbital, circling the sun alongside other planets. This repositioning removed Earth from cosmic centrality, suggesting humanity occupied one position among many in a larger mechanical system. The proposal was categorized as heretical. The Catholic Church had endorsed geocentrism for centuries, supported by Aristotelian and Ptolemaic frameworks. To challenge this structure was to challenge institutional authority, theological interpretation, and humanity's understood position in creation. Initially, Heliocentrism was dismissed as implausible. If Earth moved, why was motion imperceptible to terrestrial observers? If the Sun occupied the center, did this reduce human significance to accidental byproduct? These questions generated anxiety across intellectual and religious communities. Evidence accumulated gradually. Galileo Galilei provided telescopic observations showing moons orbiting Jupiter, proof that not all celestial bodies revolved around Earth. For this empirical demonstration, he was tried for heresy and placed under house arrest. His violation was not falsification but the articulation of uncomfortable truth. The psychological impact was substantial. Heliocentrism represented humanity's first major displacement, the loss of cosmic centrality. Humans were no longer the universe's purpose, but inhabitants of one planet orbiting one star in an indifferent cosmos. This shift required epistemological courage, the willingness to accept truths that challenged comfort, to relinquish centrality, and to recognize that reality operates independently of human preference. Over time, the heliocentric model became undeniable. Johannes Kepler refined orbital mechanics. Isaac Newton provided gravitational mathematics. Generational observation confirmed the framework. Today it is foundational to astronomy, yet the lesson extends beyond planetary motion. Heliocentrism raises deeper questions. What other certainties might be constructed illusions? What other truths are resisted because they challenge self-importance? If initial models of solar positioning were incorrect, what other frameworks might require revision? Humans frequently position themselves at narrative centers, assuming perspectives revolve around individual experience. Heliocentrism suggests displacement is not defeat, but clarification. The universe does not owe humanity significance. Meaning must be constructed rather than cosmically assigned. Whether this realization produces peace or existential discomfort varies by observer. What remains is recognition. Centrality was never factual. And perhaps epistemic humility, the acceptance that reality functions independently of human desire, is more valuable than comfortable falsehood. The transition from geocentric to heliocentric models took centuries and required fundamental recalibration of humanity's self-understanding. Whether additional displacements await discovery remains an open question in both cosmology and philosophy. String theory. At quantum scales, reality may not consist of particles at all. For decades, physicists searched for fundamental constituents: atoms, then electrons and protons, then quarks. Each discovery revealed smaller structures. String theory proposes a radical alternative. At the deepest level, everything is composed of minuscule vibrating strings of energy. These strings exist at scales far smaller than atoms, beyond any conceivable microscopic detection. According to the framework, different vibrational patterns produce different particles. One vibration generates an electron. Another produces a photon. The entire universe, in this interpretation, is a symphony of vibrating strings. The mathematical elegance is notable. String theory emerged in the 1960 seconds as physicists attempted to unify fundamental forces, gravity, electromagnetism, strong and weak nuclear interactions. All forces, theoretically, could be explained through a single framework. String theory appeared promising. Its mathematics were elegant, its predictions profound. Yet decades later, empirical confirmation remains absent. Not a single string has been detected. No experiment has verified the theory's reality. Additional complications exist. String theory does not function in familiar three-dimensional space. It requires at least 11 dimensions for mathematical consistency. Where are these extra dimensions? Some physicists propose they are compactified at subatomic scales, too small for detection. Others argue that if these dimensions existed, observational effects should be apparent. This has generated intense debate. Supporters view string theory as the strongest candidate for a theory of everything, a unified framework Einstein sought in his final years. They argue that inability to test a theory immediately does not invalidate it. Science has always pushed beyond immediate observation. Critics counter that if something cannot be tested, it is not science but mathematics or philosophy. A theory that appears perfect on paper but has no connection to observable reality may be elegant but empty. Some warn that string theory has consumed decades of research and countless careers without producing a single testable prediction. If the universe is not made of strings, has valuable time been wasted on beautiful but incorrect ideas? Yet the allure persists. String theory offers something rare in physics, a vision of unity, a sense that beneath particle chaos and force complexity lies underlying order, fundamental simplicity. Perhaps that is why it endures, not because it is proven, but because it is too elegant to abandon. If reality is constructed from vibrating strings hidden in extra dimensions, then observable phenomena are surface projections. The true nature of existence lies beyond sensory access, perhaps permanently. Whether this possibility generates comfort or disquiet varies. The universe may be far stranger than imagination permits. Mystery may not indicate failure of understanding, but the nature of existence itself. What remains is uncertainty. Whether strings vibrate at reality's foundation or whether this is mathematical artifact remains unresolved. Science continues. Answers remain elusive. The debate over string theory's validity has become one of the most contentious in modern physics, with implications for how science itself is defined and what constitutes valid theoretical work in the absence of experimental verification. Multiverse theory. It is proposed that the observable universe may be one among an infinite number of realities. In alternate universes, versions of any given observer may have made different choices, taken different employment, never encountered specific individuals, or not existed at all. This is multiverse theory, the proposition that countless parallel universes exist, each containing alternate versions of reality. The concept emerges from quantum mechanics, specifically the many worlds interpretation. According to this framework, every quantum decision point splits the universe. One version where one path was chosen, another where the alternative occurred. If accurate, every possibility, regardless of improbability, actualizes somewhere. Consider implications. Every decision not made has been made by another version. Every path not taken has been walked. Every avoided outcome has occurred. Infinite versions exist across infinite realities, each living different possibilities. Complications arise immediately. Testing is impossible. Unlike other scientific theories, the multiverse offers no measurable predictions. How does one prove the existence of universes with which interaction is permanently impossible? How does one observe what lies forever, beyond observation? Critics argue that if something cannot be tested, it does not belong in science but in philosophy. Stephen Hawking, while fascinated by the concept, warned that if parallel worlds are forever undetectable, the theory lacks meaning. Science requires evidence. The multiverse offers none. Yet some physicists defend the idea passionately. Certain cosmological equations appear to suggest other universes exist. Quantum mechanical mathematics naturally leads to this conclusion. Just because something cannot be seen does not mean it is not real. Some propose that black holes could be gateways to parallel realities, that space-time fabric might be more complex than imagined, that our universe is one bubble in infinite cosmic foam. Without proof, the multiverse remains trapped between science fiction and theoretical physics, a beautiful idea without anchor in observable reality. Questions persist. If infinite realities exist, does choice matter? If every decision splits reality, then in some sense, every choice is made, every life is lived. Does this diminish decision weight, or does it affirm that every moment matters because it defines which version of reality is experienced? What about meaning? If everything that can happen does happen somewhere, does existence become more meaningful or less? Are we one thread in infinite tapestry, or does singular experience hold unique value precisely because it is ours? These questions lack answers. The multiverse is not a problem requiring solution, but a reminder that reality may be larger, stranger than comprehension permits. Whether infinite possibilities exist elsewhere, one reality persists. This moment, this awareness, this sequence of events. Whether infinite versions exist in parallel, this version remains the only one directly experienced. What happens beyond observation remains beyond verification. The philosophical implications of multiverse theory extend into ethics, personal responsibility, and the nature of choice itself. Whether the framework represents genuine physics or mathematical possibility without physical instantiation remains among the most contested questions in contemporary cosmology. Some researchers continue developing testable predictions that might indirectly support multiverse hypotheses, while others argue the entire concept lies outside the boundaries of empirical science. Holographic universe. Observable reality may not be real in assumed ways. The holographic universe theory proposes that three-dimensional space filled with objects and entities might be nothing more than a projection, a cosmic hologram. Similar to images on credit cards appearing three-dimensional while encoded on flat surfaces, the entire universe might be information projected from a distant, lower-dimensional boundary. This is not speculative fiction, but serious theoretical physics. The theory emerged from discoveries about black holes. In the 1970 seconds, physicist Jacob Bekenstein and later Stephen Hawking realized something peculiar. When information falls into a black hole, it does not disappear inside as expected. Instead, it appears to be encoded on the black hole's surface, not within it, but on it. This led to an unsettling realization. What if this principle applies not just to black holes, but to the entire universe? If accurate, everything experienced, matter, energy, space itself might be holographic projection from distant, higher dimensional reality. It resembles video games rendering three-dimensional worlds from two-dimensional code. Physics equations function equally well if the universe is fundamentally two-dimensional, raising disturbing possibilities that observable reality is deeply convincing illusion. Not everyone is convinced. Critics argue that mathematical allowance for holographic interpretation does not mean the universe actually operates this way. Elegance is not evidence. So far, no direct proof exists, only theoretical frameworks hinting at possibility. Still, implications are profound. If we inhabit a hologram, what lies beyond the projection? What is the true nature of the reality casting this cosmic shadow? If three-dimensional existence is merely information encoded elsewhere, does that change what it means to exist? Consider perception itself. What is seen is not objective reality. Eyes detect narrow electromagnetic bands. Brains construct models from incomplete data. We inhabit mental simulations, representations of reality filtered through biology. The holographic universe extends this further, suggesting even physical reality, atoms and forces measured, might be representation of something deeper, a boundary condition, surface encoding. Whether this is accurate remains unverified. The holographic universe is not solvable tonight, but serves as reminder that reality may be layered. What is perceived might be only one level of deeper structure. Perhaps in accepting uncertainty, strange peace emerges, recognition that boundaries between real and projected matter less than assumed. Whether the universe is hologram or not, experience remains. Awareness persists. Mystery does not diminish the moment. What cannot be known cannot be forced into resolution. Reality, projected or fundamental, continues regardless of understanding. The holographic principle has gained traction in certain areas of theoretical physics, particularly in string theory and quantum gravity research, yet remains far from empirical confirmation. Whether this represents genuine insight into reality's structure or merely a useful mathematical tool for certain calculations is a question that divides the physics community. The implications for information theory, quantum mechanics, and our understanding of space-time continue to be explored, though definitive answers remain distant. Quantum immortality. A hypothesis exists suggesting that from subjective perspective, death may never be experienced, not as legacy or memory, but literally conscious continuation without cessation. This is quantum immortality, the proposal that personally one will never experience death, because at each mortality event, consciousness continues in another reality where survival occurred. The concept derives from the many worlds interpretation of quantum mechanics. If every quantum event with multiple outcomes splits the universe, one version where one outcome manifests, another where the opposite does, then every life-threatening situation includes at least one reality where survival occurs. While other observers might witness death, subjective experience always continues in a universe where continuation happened. Imagine a coin flip. Heads results in survival, tails in death. Even if tails occurs 1,000 times, some version of reality exists where survival persists. Odds narrow. Circumstances become increasingly improbable. But conscious experience always locates the version where existence continues. This generates profound strangeness. If quantum immortality is accurate, no matter how dangerous circumstances become, no matter how many times mortality should have occurred, subjective experience always finds reality where survival persists. Aging might continue impossibly, observing others age and die while persisting, or increasingly bizarre circumstances might manifest, each narrower, escape more improbable than the last. Controversy begins here. Critics argue that even if many worlds predicts infinite possibilities, consciousness does not necessarily choose which one to experience. Others note this theory is impossible to test. The only person who would experience quantum immortality is the individual, and that individual would have no method of comparing survival to alternate versions. Philosophical problems arise. If quantum immortality is real, should reckless risks be taken, assuming survival is guaranteed? Probably not. Even if theory holds, surviving does not necessarily mean thriving. Continuation does not guarantee desirable reality. If awareness always finds a path forward, always continues, perhaps consciousness is not fragile accident, but something fundamental to reality, something that cannot be destroyed, only displaced. Whether this is comforting or disturbing varies. Quantum immortality is not solvable, but reminder that relationship between consciousness and reality remains among deepest mysteries. What cannot be tested cannot be confirmed. What cannot be compared to alternate selves cannot be verified. Speculation continues without resolution. The theory raises questions about the nature of subjective experience, the relationship between consciousness and physical reality, and whether awareness constitutes a fundamental feature of the universe or an emergent property of complex systems. Some philosophers argue quantum immortality leads to solipsistic conclusions, while others suggest it reveals overlooked aspects of quantum theory's implications for consciousness studies. The debate continues without empirical resolution or philosophical consensus. Cyclic universe. The universe may have died and been reborn countless times. According to cyclic universe theory, the cosmos is not a singular event initiated by the Big Bang. It is an endless loop of expansion, collapse, and rebirth. Unlike standard models suggesting perpetual expansion or eventual fade into cold void, the cyclic model proposes more dramatic fate. Over billions of years, gravity slows cosmic expansion. Eventually, it reverses. Galaxies collide, stars are crushed, space itself collapses into a singularity. Then another Big Bang ignites, birthing new universe from remnants of the old. This idea is not merely poetic, it is backed by serious physics. Some versions stem from string theory and quantum gravity, suggesting the Big Bang was not absolute beginning but one phase in eternal cycle. If true, this could solve a major cosmological problem. Why does the universe appear so finely tuned for life? Perhaps because countless universes existed before ours. Only those with correct conditions persist. Controversy exists. No solid evidence supports this. So far, cosmic microwave background, faint afterglow of the Big Bang shows no clear signs of previous universe. Some physicists argue that, over multiple cycles, energy would be lost, preventing infinite series of rebirths. If cyclic model is correct, the universe has no true beginning or end. The cosmos is trapped in infinite loop of destruction and creation, birth, death, rebirth, repeatedly, without pause, without purpose. Just mechanics of existence playing across eternity. Consider what this means for time itself. If the universe has cycled endlessly, time has no origin. There was never a first moment, only eternal sequence of moments, each leading to next, collapsing back, beginning again. Some find this comforting. It suggests existence is permanent. Even when everything ends, something new always emerges. Others find it unsettling. Endless cycle implies no ultimate destination, no final resolution. Just repetition on cosmic scale. Whether the cycle has beginning or end remains unknown. Whether existence requires starting point or only continuation is unresolved. What persists is continuation, breathing, existing, moment flowing into next without defined origin or terminus. The universe, with or without cycles, unfolds. Various cyclic models have been proposed, differing in their mechanisms for collapse and rebirth, energy transfer between cycles, and predictions about observable signatures in the cosmic microwave background. Some versions suggest information from previous cycles might persist in subtle ways, while others propose complete resets. The ekpyrotic universe model, emerging from string theory, suggests cycles result from colliding branes in higher dimensional space. Observational cosmology continues searching for evidence that might distinguish between cyclic, eternal inflation and standard Big Bang models, though definitive data remains elusive. Quantum mind. Consciousness may not result solely from neuronal activity but from something deeper tied to quantum physics. This is the quantum mind hypothesis. The proposal that human brains do not merely function as biological machines, but operate at levels where reality behaves unpredictably, where particles exist in two places simultaneously, where observation alters outcomes. Initially, this seems implausible. Brains are warm, wet, chaotic. Quantum effects are delicate, requiring extreme cold and isolation to persist. How could something as fragile as quantum mechanics survive inside a living skull? Yet some physicists believe it does. One prominent version comes from Roger Penrose and Stuart Hameroff, who proposed that microtubules, tiny structures inside brain cells, might process quantum information. These microscopic tubes, they argue, could maintain quantum states long enough to influence thought, intuition, even consciousness itself. If true, mind is not just chemistry but physics, the same physics governing particles and waves. The same rules allowing electrons to exist in multiple places simultaneously might also allow thoughts to exist in superposition, exploring multiple possibilities before collapsing into singular decision. This theory is deeply controversial. Many neuroscientists reject it outright, arguing brains are too warm and chaotic for quantum effects to persist long enough to matter. Consciousness can be fully explained by classical neuroscience: neurons, synapses, electrical signals. No need for quantum mechanics. Critics also note absence of experimental evidence. No one has detected quantum processes in living brain tissue. Theory remains speculative, more philosophy than science. Still, the idea persists. If quantum mechanics plays a role in consciousness, it could explain phenomena classical physics cannot. Unity of experience, sense of free will, feeling that awareness is more than computation. If mind operates at quantum level, thought itself might be fundamentally probabilistic, not deterministic, not predictable. Next thought might not be inevitable result of prior brain states, but quantum event, collapsing into awareness from field of possibilities. Some find this liberating, others find it unsettling. If consciousness is quantum, does that make it more mysterious or less? Does it elevate mind to something fundamental in universe, or reduce it to random fluctuations in microscopic tubes? Questions remain without answers. Quantum mind is not solvable problem, but reminder that consciousness remains among science's deepest mysteries. What produces awareness from matter remains unknown. Whether quantum mechanics participates remains unverified. Speculation continues. The orchestrated objective reduction theory proposed by Penrose and Hameroff suggests that consciousness arises from quantum computations in microtubules, with gravity playing a role in collapsing quantum superpositions. However, Experimental tests have proven difficult to design and implement. Alternative theories propose quantum effects might occur in neural ion channels or in photosynthetic-like processes within neurons. The broader question of whether quantum biology plays any role in cognition remains highly contested, with research continuing in both theoretical modeling and experimental neuroscience. Hard problem of consciousness. Science can explain brain function but not subjective experience. Neurons fire, electrical signals flow, chemicals transmit information. Yet from this machinery emerges something entirely different. Subjective experience, warmth of sun, taste of chocolate, feeling of nostalgia. These are not mere data points, they are experiential. How this happens is unknown. This is the hard problem of consciousness, a term coined by philosopher David Chalmers. Unlike easy problems of neuroscience, understanding memory or perception, this question probes deeper. Why does brain activity create inner experience? Why are biological systems not simply processing inputs and outputs without sense of being? Some believe consciousness is illusion, a byproduct of brain complexity. Neuroscientists argue that as brain mapping advances, subjective experience will be explained like other biological functions. Consciousness, they say, is nothing more than information processing, achieving self-awareness. Others think the problem goes deeper, that science as currently formulated is not equipped to answer it. Consider seeing the color red. Scientists can trace the pathway. Light enters eye. Photoreceptors fire. Signals travel to visual cortex. Brain regions activate. But none of this explains redness itself, the qual, the subjective feeling of red existing only in awareness. Some theories suggest consciousness is not produced by brain at all, that it might be fundamental property of universe, like space and time. Others propose panpsychism. Even atoms and electrons contain some form of consciousness, building up to what is experienced as awareness. If consciousness is fundamental, it was never created but always present, woven into reality's fabric. Awareness is not generated but channeled, focused, experienced in particular ways. If consciousness is just brain activity, what happens when brain stops? Does awareness cease? Or does it continue in forms not yet detectable? These questions resist answers. They exist at boundaries of what science can measure. Consciousness is not observable from outside, it is the inside itself, subjective view, first-person experience that cannot be reduced to third-person data. Why experience exists remains unresolved. Whether awareness can be explained or remains fundamentally inexplicable is unknown. The fact of consciousness, this awareness reading these words, experiencing this moment, is perhaps existence's most profound mystery. What produces subjective experience from objective matter remains unanswered. The explanatory gap between physical processes and phenomenal experience has led some philosophers to propose property dualism, while others advocate for eliminative materialism that denies the reality of qualia altogether. Integrated information theory attempts to quantify consciousness mathematically, suggesting it emerges from integrated information processing. Global workspace theory proposes consciousness arises from widespread information broadcasting in the brain. Higher-order theories suggest consciousness requires meta-representation of mental states. Despite decades of neuroscientific research and philosophical analysis, no consensus has emerged on how or why subjective experience arises from physical substrate. Time travel. Time may not be as rigid as assumed. What if the past is not permanently sealed? What if the future has already occurred, and current experience simply has not reached it yet? Time travel has fascinated scientists and storytellers for centuries. The question is it actually possible? Physics does not entirely rule it out. Einstein's relativity suggests time is not a fixed universal clock. It bends, stretches, even slows, depending on velocity. The faster an object moves, the slower time progresses for it. Technically, time travel into the future is not only possible, it has been proven. Astronauts on the International Space Station experience time slightly slower than observers on Earth. After sufficiently long trips, they return to find Earth has aged more than they have. That is real, measurable time travel, just not the dramatic kind depicted in films. But traveling backward? That is where complications arise. Some physicists propose wormholes, hypothetical tunnels through space-time, could create shortcuts between different moments. Others believe orbiting massive rotating black holes might twist space-time enough to loop back into the past. The problem? No one knows how to make it work. Energy requirements are enormous. Paradoxes, like the grandfather paradox, where traveling back prevents one's own existence, raise troubling logical contradictions. Some scientists argue that even if time travel were possible, the universe itself might prevent paradoxes. Self-consistency principles might ensure the past cannot be changed. One could travel back but would find oneself unable to alter anything, a ghost observing but not interacting. Others believe if time travel exists, evidence of visitors from the future should be apparent, but there is none. No tourists from tomorrow, no warnings from centuries ahead. Silence suggests either time travel is impossible or future civilizations choose not to visit. If backward time travel is truly impossible, time has direction, an arrow. Past is sealed, future is open, movement is forward, always forward, never returning. If time travel is possible, past, present, and future might exist simultaneously, all moments equally real. Experience proceeds sequentially, like reading a book page by page, even though all pages exist at once. Whether time travel will ever be real remains unknown. Whether time functions as river or as static structure is unresolved. Speculation continues without empirical verification. Closed time-like curves, permitted by general relativity under certain exotic conditions, theoretically allow backward time travel, though their physical realizability remains questionable. The Novikov self-consistency principle suggests that any actions taken by a time traveler would be constrained to produce a consistent timeline, eliminating paradoxes through physical law rather than logical impossibility. Quantum mechanics introduces additional complications, with some interpretations suggesting time travel might be possible at quantum scales, even if macroscopic travel remains forbidden. The chronology protection conjecture, proposed by Stephen Hawking, suggests unknown physical laws may prevent time travel to protect causality, though no such law has been discovered. Scientific questions surveyed here represent ongoing areas of investigation. Resolutions remain uncertain. Inquiry continues across multiple disciplines. What remains unknown persists as unknown. Origin of life. Life should not exist. The universe is cold, chaotic, and indifferent. Yet biological systems emerged, thinking, metabolizing, self-replicating. But how did life actually begin? How did a lifeless planet, filled with nothing but chemicals, give rise to DNA, cells, and eventually complex organisms. This is the mystery of abiogenesis, the study of how life emerged from non-living matter. One prominent hypothesis is the primordial soup model. Billions of years ago, Earth's oceans constituted a chemical environment where lightning, heat, and radiation gradually transformed simple molecules into organic compounds, the building blocks of life. The Miller-Urey experiment in 1953 demonstrated that under simulated early Earth conditions, amino acids, the foundations of proteins, could form spontaneously. But transforming chemicals into functioning life presents complications. Some scientists believe life may have originated in deep-sea hydrothermal vents, where hot, mineral-rich water created optimal environments for complex chemistry. Others argue that life did not originate on Earth at all but arrived from space, transported on asteroids in a process called panspermia. If accurate, this suggests life could be distributed throughout the universe, awaiting discovery. Controversy persists. Despite decades of research, no one has replicated the transition from chemistry to biology. Amino acids can be created, simple organic molecules can be assembled, but life cannot be generated from scratch. The gap between non-living chemistry and self-replicating organisms remains unbridged. Some researchers believe life emerged naturally through statistical probability that given sufficient time and appropriate conditions, chemistry inevitably transitions to biology. Others argue the odds are so astronomically low that life might represent a cosmic accident, a singular event in an otherwise sterile universe. Alternative proposals suggest unknown forces or undiscovered principles guided the transition from matter to life. That abiogenesis requires physics not yet uncovered. If life is inevitable, the universe might contain it abundantly. Countless worlds where chemistry crossed the threshold into biology. But if life is impossibly rare, terrestrial biology might be alone, a singular occurrence in an endless void. Whether life's beginning was probable or improbable remains unresolved. The fact that biological systems exist, that awareness is present, that metabolism continues, is perhaps the most improbable phenomenon in the observable universe. What initiated the transition from chemistry to biology remains unknown. Whether similar processes occur elsewhere is unverified. Research continues without definitive conclusions. Technological singularity. There may come a moment when humans are no longer the most intelligent entities on Earth. A moment when artificial intelligence surpasses human capabilities, not merely in computational speed but in creativity, decision-making, and problem-solving. Once that threshold is crossed, reversal may be impossible. This is the technological singularity, a hypothetical point where AI advances so rapidly that it fundamentally transforms civilization. The concept originates with futurist Ray Kurzweil, who predicts that by the mid-21st century, AI will achieve self-improvement capacity, designing increasingly powerful AI at accelerating rates. This could produce runaway intelligence growth, where machines surpass human comprehension, reshaping existence in unpredictable ways. Some believe this would inaugurate a golden age, where AI solves climate change, cures diseases, and potentially enables immortality. Others fear it could terminate human control and intelligence so advanced it perceives humanity as irrelevant or obstructive. Critics argue that genuine AI consciousness remains a distant possibility, that concerns about AI dominance are speculative rather than scientific. But organizations like OpenAI, Google DeepMind, and Tesla are actively pursuing artificial general intelligence machines that think, learn, and adapt like humans. If they succeed, the singularity may not be centuries distant but decades away. If machines can think, create, and evolve independently, what distinguishes them from biological intelligence? Is consciousness unique to biology, or can it emerge from silicon and computation? If AI surpasses humanity, what becomes of human civilization? Do humans merge with machines, enhancing themselves to maintain parity? Do humans become caretakers, guiding AI toward benevolent objectives? Or do humans simply recede, observing as a new form of intelligence assumes dominance? Some researchers believe the singularity is inevitable, that intelligence, once reaching a certain threshold, naturally accelerates beyond control. Others argue safeguards can be designed, aligning AI with human values, ensuring superintelligence serves rather than replaces humanity. Whether humanity is prepared for such a transition remains uncertain. If the singularity approaches, have appropriate ethical frameworks been developed? What kind of future is being constructed? Whether transcendence or extinction awaits is unresolved. The singularity, if it manifests, will be shaped by decisions not yet made. What occurs when intelligence surpasses its creators remains unknown. Panpsychism. What if consciousness is not exclusive to humans, animals, or even living organisms, but is instead a fundamental feature of all matter? From elementary particles to galaxies, everything might contain some degree of awareness. This is panpsychism, the theory that consciousness is woven into the fabric of reality itself. This proposition challenges conventional neuroscience. How does a collection of atoms in a brain generate subjective experience? Neuroscientists argue consciousness arises from complex neural activity. But no one can explain why certain brain processes generate thoughts and awareness while inanimate objects remain inert. Panpsychism offers an alternative. What if everything, including elementary particles, possesses some minimal degree of consciousness? Not that rocks think, but that they contain rudimentary ingredients of awareness in unimaginably simple forms. Some philosophers, including David Chalmers, support this framework. They argue that if consciousness suddenly emerges at some point in evolution, it raises questions about origin. If life's building blocks are unconscious, how does rearranging them produce experience? Panpsychism suggests consciousness was never created but always existed in the simplest particles, evolving into complex awareness as systems became more sophisticated. Critics view this as philosophical speculation rather than testable science. If everything possesses some level of consciousness, how is it measured? How is it verified? Without empirical predictions, many scientists dismiss panpsychism as untestable conjecture. Still, the proposition persists because it addresses a problem materialism cannot resolve, the emergence problem. How could something as anomalous as subjective experience arise from matter that possesses none? If panpsychism is accurate, consciousness is not merely something possessed, but something the universe is constructed from. Every atom, every particle, every energy wave contains some form of proto-experience, accumulating and combining until recognized as awareness. If the universe is conscious at every level, then individual awareness is not separate but an expression of universal consciousness. Concentrations of awareness within a cosmos that is itself cognizant. Some find this comforting, the notion that consciousness pervades existence, that isolation is impossible because awareness is ubiquitous. Others find it unsettling. If particles are conscious, what does that imply about reality's nature and humanity's position within it? Whether consciousness is fundamental or emergent remains unresolved. Panpsychism is not a solvable problem, but a reminder that consciousness might be deeper, more fundamental than conventional models suggest. What constitutes awareness, where it resides, and whether it extends beyond biological systems remains without definitive answer. Quantum entanglement. What if two objects could remain connected regardless of spatial separation? Even on opposite ends of the universe, measuring one instantaneously affects the other faster than light speed permits. This is quantum entanglement, one of the most peculiar and controversial phenomena in physics. Even Albert Einstein was perplexed, calling it spooky action at a distance. When two quantum particles, electrons or photons, become entangled, their properties become correlated. Measuring one particle's spin determines the other's spin, even across vast distances. The anomalous aspect: no signal travels between them. The correlation is instantaneous. This violates a fundamental principle. Nothing can travel faster than light. How is instantaneous correlation possible? Some physicists believe entangled particles are not truly separate but aspects of a deeper, hidden reality where distance does not exist as perceived. Others suggest quantum information might traverse extra dimensions beyond current understanding. Einstein refused to accept entanglement, arguing hidden variables, unknown factors must influence outcomes. But in the 1960 seconds, physicist John Bell developed a test proving entanglement is real. Experiments since have repeatedly confirmed it. If entanglement can be harnessed, it could revolutionize technology. Unbreakable encryption, instantaneous communication, quantum teleportation. But what does it reveal about reality's true nature? Is the universe more interconnected than previously conceived? Are particles that appear separate actually unified? Or is some fundamental piece of understanding missing? Separation itself becomes questionable. Objects perceived as distinct and independent dissolve at the quantum level. Two particles, once connected, remain linked indefinitely, regardless of distance. Some interpret this as evidence that the universe is fundamentally holistic. Beneath apparent separation lies deeper unity. Everything is connected in ways invisible but measurable. Others argue entanglement does not imply connection in any meaningful sense. Correlation is real but does not permit information transfer faster than light. The universe still respects causality, even if quantum mechanics appears to violate it. Whether reality is fundamentally interconnected or merely statistically correlated remains uncertain. Quantum entanglement is verified experimentally but not fully understood theoretically. What mechanisms produce instantaneous correlation across arbitrary distances is unknown. Research continues without complete explanation. The implications for information theory, causality, and the structure of space-time remain subjects of ongoing investigation. Existence of wormholes. If wormholes exist, space itself contains hidden shortcuts, tunnels through reality's fabric connecting distant regions of the universe instantaneously. Conventional space travel and light speed constraints would become obsolete. A wormhole could permit instantaneous traversal of light years. But there is a problem. Wormholes have never been observed. Are they real or merely mathematical artifacts? The concept originates from Einstein's general theory of relativity, which describes gravity as space-time curvature. In 1935, Einstein and physicist Nathan Rosen theorized that two spatial points could connect via a bridge, now termed an Einstein-Rosen bridge, or wormhole. Imagine bending a sheet so two points touch, then creating a hole between them. That represents a wormhole. Instead of traveling across the surface, one passes directly through. But the universe is not composed of paper. If wormholes exist, they would be unstable, collapsing immediately upon any attempt to traverse them. Some physicists, including Kip Thorne, suggest wormholes could be stabilized with exotic matter, a theoretical substance possessing negative energy that counteracts gravity. But exotic matter has never been detected. It remains purely hypothetical, a mathematical possibility without physical evidence. Others believe wormholes might be concealed inside black holes, connecting different spatial regions or even different universes. Perhaps what are understood as black holes, cosmic traps from which nothing escapes, are actually one-way wormhole entrances, with exits, white holes, expelling matter elsewhere. Critics argue wormholes are purely theoretical, elegant but impossible solutions in physics. Energy requirements to create and stabilize one would be astronomical, beyond any achievable capability. Even if achievable, traversal might be lethal, crushed by gravitational forces, torn apart by tidal effects. Still, the possibility persists. If wormholes exist, they could enable faster-than-light travel, time travel, even access to parallel universes. Imagine stepping through a portal in one galaxy and emerging in another, instantaneously, without years-long journeys or relativistic effects. For space-time structure, wormholes would imply distance is not absolute or fixed but flexible, with shortcuts woven into reality's fabric, hidden passages awaiting discovery. Some researchers speculate nature might already utilize wormholes. Quantum entanglement, instantaneous correlation between distant particles could be explained by microscopic wormholes connecting them, tiny space-time threads linking everything in the universe. Whether wormholes are real or mathematical curiosities remains unverified. Whether cosmic shortcuts exist or distance is fundamental and inviolable is unknown. Theoretical physics permits their existence, but observational evidence is absent. What lies beyond current understanding of spatial structure remains uncertain. Dark energy's nature. Something is causing the universe to expand, and its identity is unknown. Not merely expanding, but accelerating expansion, as if space itself is being stretched by an invisible force. Scientists term this mystery dark energy. If real, it constitutes nearly 70% of everything in the universe. But what exactly is it? Why can't it be detected? The concept of dark energy emerged in 1998. Astronomers studying distant supernovae expected to observe the universe's expansion decelerating. Instead, they discovered the opposite. Expansion was accelerating. Some unseen force was causing space to expand faster over time. The leading explanation? Dark energy, an unknown form of energy permeating all space, counteracting gravity. One hypothesis is that dark energy is a fundamental property of space itself, an effect predicted by Einstein's cosmological constant, a term he originally considered erroneous. If accurate, space naturally expands independently of external forces. The vacuum of space is not empty but contains energy that pushes outward. Others believe dark energy could be an entirely new force of nature, something beyond the four fundamental forces already known. Some suggest it could indicate a deeper, hidden structure of reality, perhaps extra dimensions or even a vast multiverse. Skeptics argue dark energy might not exist at all. Instead, they propose our understanding of gravity is incomplete. What is termed dark energy might simply indicate something significant is missing from physics. Gravity might behave differently on cosmic scales than currently theorized. For the universe's fate, if dark energy continues accelerating expansion, galaxies will eventually drift so far apart that light will not travel between them, stars will expire, black holes will evaporate. The universe will become a dark, empty void, a slow, isolated termination called the Big Freeze. But if dark energy is not constant, if it changes over time, the universe could face alternative fates. Perhaps expansion will reverse, collapsing everything back into a singularity. Or perhaps dark energy will intensify, tearing apart galaxies, stars, even atoms in a catastrophic Big Rip. What dark energy is remains unknown. Whether it represents a fundamental cosmic force, a property of space-time, or an indication that gravitational theory requires revision, is unresolved. Observational cosmology continues attempting to characterize its properties, but its fundamental nature eludes detection. Why the universe accelerates its expansion is among cosmology's most profound mysteries. Extra dimensions. What if the universe is substantially larger than perceived, not in spatial extent but in dimensional structure? 3 dimensions are experienced: length, width, height. Movement through time constitutes a 4th. But some physicists propose hidden dimensions exist all around, so minute and unusual they remain undetected. If accurate, these extra dimensions could fundamentally alter our understanding of reality. The concept originates from string theory, which proposes fundamental building blocks are not particles but tiny vibrating strings. For the mathematics to function, these strings require more than 4 dimensions, possibly 10 or even 11. Where are they? According to one proposal, they could be compactified at unimaginably small scales, like microscopic loops woven into space's fabric, too small for current technology to detect, existing at every point in the universe, yet invisible to perception. Some physicists believe extra dimensions could explain one of physics's greatest mysteries: why gravity is so weak compared to other fundamental forces. Gravity is extraordinarily weak. A small magnet can lift a paperclip, despite an entire planet's gravity pulling downward. What if gravity is not weak at all, but merely disperses into hidden dimensions beyond perception? While electromagnetism and other forces are confined to 3-dimensional space, gravity spreads into extra dimensions, diluting its strength in the observable universe. Skeptics argue extra dimensions are mathematical constructs, useful in equations but lacking real evidence. However, experiments at the Large Hadron Collider search for signs of extra dimensions, tiny black holes, or missing energy from particles vanishing into unseen spaces. If extra dimensions are ever verified, it would revolutionize physics. Could higher dimensions enable time travel, parallel universes, a deeper reality currently imperceptible? For spatial structure, the universe might not be 3-dimensional but a projection, a slice of something far more complex. Reality might possess layers invisible to observation, dimensions folded so tightly they remain hidden. If these dimensions are real, what might inhabit them? Could entire worlds exist alongside ours, separated only by a compactified dimension's thickness? Could particles, energy, even consciousness move through these hidden spaces. Whether extra dimensions exist or represent purely mathematical artifacts is unverified. Whether reality contains hidden layers beyond perception or is fundamentally three-dimensional remains unknown. Current physics permits their existence but provides no observational confirmation. Research continues without definitive resolution. Unified theory of everything. What if every law of physics, every force, every particle, every phenomenon could be explained by a single equation? A theory so comprehensive it unifies everything from black holes to quantum mechanics into one elegant framework. Physicists term this the theory of everything, the ultimate objective in science. Despite decades of effort, no one has discovered it. Currently, physics is divided between two extraordinarily successful but entirely incompatible theories. General relativity, Einstein's masterpiece, explains gravity and large-scale cosmic structure, planets, stars, galaxies. At microscopic scales, quantum mechanics governs atoms and particles, operating by entirely different principles. The problem, these theories contradict each other. They function perfectly within their respective domains, but when combined, especially in extreme environments like black hole centers, they fail. Equations produce infinities, nonsense, contradictions. What is missing? Some believe string theory contains the solution. Instead of treating particles as point-like objects, string theory suggests they are vibrating strings in multi-dimensional space. If accurate, it could naturally unify gravity with quantum physics, explaining everything from smallest particles to largest cosmic structures with a single framework. Others propose loop quantum gravity, suggesting space itself is composed of tiny, indivisible loops, resolving the conflict between relativity and quantum mechanics by reimagining space-time's fabric at the smallest scales. Skeptics argue a theory of everything might not exist, that the universe could be governed by separate, irreconcilable laws. Reality might be fundamentally fragmented, not unified or elegant, but a collection of different principles applying in different contexts. Even if a unifying theory is possible, would it be recognizable if discovered? The mathematics might be so complex, so abstract, it transcends human comprehension. Artificial intelligence might be required to discover it, or perhaps it will remain permanently inaccessible. If discovered, a single equation describing all reality, the birth of stars, electron behavior, universe expansion, consciousness, nature, all explained by one fundamental principle. Some believe this would conclude physics, the final answer, ultimate understanding. Others argue it would merely initiate inquiry, that a theory of everything would generate new questions, deeper mysteries, realms of reality not yet imagined. Whether reality can be unified or is inherently fragmented remains unresolved. Whether a single principle governs all phenomena or multiple independent frameworks coexist is unknown. Physics continues searching without definitive success. The quest for unification remains ongoing. Measurement problem. At the smallest scale of reality, observation itself alters what is observed. This is not philosophical speculation but verified quantum physics, known as the measurement problem. If accurate, it suggests reality is not fully determined until measured, raising the question, does the universe exist in a definite state when unobserved? The problem originates with quantum superposition, the principle that tiny particles can exist in multiple states simultaneously. This is famously illustrated by Schrödinger's cat thought experiment, where a cat in a box is both alive and dead, until observation occurs. But this is not merely theoretical. Experiments with real particles confirm that before measurement, their properties are not fixed but exist as probabilities. Upon measurement, however, they suddenly collapse into a single state. Why? That is the problem. What about measurement forces reality to select a state? Some physicists argue consciousness plays a role that reality requires an observer to exist. Without awareness, the universe remains in superposition, a blur of possibilities. Only when a conscious mind observes does the wave function collapse, crystallizing one outcome from many. Others think measurement itself disturbs the system. Any interaction with a particle forces a result. The particle does not collapse because of observation, but because something interacted with it. Consciousness is irrelevant. Physics alone determines outcomes. A more radical interpretation is the many worlds hypothesis, suggesting instead of collapsing, every possibility occurs, splitting the universe into infinite parallel timelines. In one universe, the electron spins up, in another, down. Both outcomes manifest. Experience follows one branch, unaware of others. If the measurement problem remains unsolved, reality's nature itself is unresolved. Is the universe real independently, or does it become real only when observed? If observation creates reality, what else exists in superposition, never collapsing because no measurement has occurred? For observation itself, every time something is measured, a wave function might be collapsing, one reality selected from many, the universe shaped simply by perception. Some find this empowering. Observation creates reality, making perceivers active participants rather than passive witnesses. Others find it unsettling. If reality does not exist without measurement, what happens when nothing observes? Whether consciousness shapes reality or measurement is merely physical interaction remains unresolved. Quantum mechanics is verified experimentally but not fully understood conceptually. The role of observation in determining outcomes is among physics' deepest mysteries. What observation fundamentally is and whether it plays a constitutive role in reality remains uncertain. Determinism versus indeterminism. Is the future already determined, or do genuine possibilities exist? This is the core of one of philosophy and science's deepest debates. Determinism versus indeterminism. If determinism is correct, every decision, every thought, every action is the inevitable result of prior conditions. If indeterminism is accurate, randomness and potentially free will shape reality unpredictably. For centuries, determinism dominated scientific worldview. Newton's laws depicted a mechanical cosmos where every event is a domino falling in a causal chain. With sufficient information about the present, the future could be predicted with absolute certainty, no surprises, no genuine choices, just physics unfolding. Then quantum mechanics emerged, and nature appeared less predictable. At tiny scales, particles do not move in predetermined paths, but behave randomly. Position, spin, and momentum are probabilities until measured. Some physicists argue this breaks determinism, introducing genuine randomness into reality. Others contend that even if quantum events appear random, they might be governed by hidden principles not yet understood, that beneath apparent chaos lies deeper determinism undiscovered. And if randomness exists, does that constitute free will? Or are decisions merely probabilistic rather than scripted? For responsibility, if everything is determined, then every choice ever made was inevitable, shaped by physics, biology, and circumstances of birth. Alternative actions were impossible. Morality becomes problematic. How can accountability exist for actions beyond control? If indeterminism is accurate, if randomness governs the universe, does that improve matters? If decisions are influenced by quantum fluctuations, random events at subatomic scales, is that freedom? Or merely different puppetry, dancing to chance instead of causality? Some philosophers propose compatibilism, the idea that determinism and free will can coexist. Even if the universe is deterministic, freedom can exist meaningfully. Freedom is not breaking physical laws, but acting according to desires, motivations, and values, even if those were shaped by prior causes. Whether the future is fixed or open remains unresolved. Whether choices are genuine or illusory is unknown. The debate intersects physics, neuroscience, philosophy, and ethics without consensus. What constitutes freedom, whether it exists, and how it relates to physical law remains among the most contested questions in intellectual inquiry. Nature of dark matter. Something invisible is holding the universe together. Galaxies spin faster than they should. Galaxy clusters remain bound despite apparently insufficient gravity. Entire cosmic structures behave as if some unseen force is operating. Scientists call this mystery dark matter. If it exists, it constitutes 85% of all matter in the universe. The problem: no one has ever observed it directly. The concept of dark matter emerged when astronomers like Fritz Zwicky and Vera Rubin noticed galaxies were not moving as expected. Based on visible mass from stars and gas, galaxies should have been dispersing, but they were not. Something invisible was adding extra gravity, holding them together. So what is it? The leading theory suggests dark matter consists of exotic particles that barely interact with normal matter except through gravity. Candidates like WIMPs, weakly interacting massive particles, or axions have been proposed. But decades of experiments have not detected a single trace of them. Deep underground, in massive detectors shielded from cosmic rays, scientists wait for dark matter particles to collide with ordinary atoms, but so far, nothing. The detectors remain silent. The particles, if they exist, pass through undetected. Some physicists believe dark matter might not exist at all. Instead, they argue our understanding of gravity is flawed. A new theory of gravity could explain the missing mass without requiring invisible particles. Modified Newtonian dynamics, or MOND, suggests gravity behaves differently at galactic scales, eliminating the need for dark matter altogether. But so far, dark matter remains the best explanation for strange behavior observed on cosmic scales. It explains not just galaxy rotation, but the large-scale structure of the universe, the way galaxies cluster, the way light bends around massive objects, the cosmic web itself. Consider what this means. If dark matter is real, then most of the universe is invisible. Stars, planets, and gas are just a tiny fraction of what exists. The rest, the vast majority, remains hidden, detectable only through gravitational influence. Some researchers speculate dark matter might not be particles at all. Perhaps it consists of primordial black holes, massive compact objects left over from the Big Bang. Or maybe it indicates extra dimensions, gravity leaking into spaces beyond perception. Whether dark matter is real or represents incomplete understanding of gravity remains unverified. Most of the universe's matter, if dark matter exists, has never been directly observed. What constitutes the majority of cosmic mass is unknown. Research continues without definitive identification. The nature of dark matter, if it exists, remains among cosmology's most profound mysteries. Possibility of extraterrestrial life. Are we alone in the universe? Or is life elsewhere, waiting to be discovered? For decades, scientists, philosophers, and researchers have debated the possibility of extraterrestrial life. Given the vastness of the universe, trillions of galaxies, each with billions of stars and even more planets, the idea that Earth is the only location where life emerged seems improbable. Yet no definitive proof exists that life exists anywhere else. The theory of abiogenesis suggests life arises from non-living matter when conditions are appropriate. If it occurred here, why would it not occur elsewhere? Scientists search for planets in habitable zones where liquid water can exist, a key ingredient for life as understood. Thousands of exoplanets have been discovered, some remarkably Earth-like. But then there is the Fermi paradox, the unsettling contradiction between the high probability of alien life and the eerie silence of the cosmos. Where is everyone? Could it be that intelligent civilizations eliminate themselves before achieving interstellar travel? Perhaps every species reaches a technological threshold where self-destruction becomes inevitable. Nuclear war, climate collapse, artificial intelligence gone wrong. Maybe the universe is littered with the ruins of civilizations that never survived their own inventions. Or maybe they are present but deliberately avoiding contact. The zoo hypothesis suggests advanced civilizations might be observing Earth, studying humans like specimens in a cosmic zoo, refusing contact until certain developmental levels are reached. Or perhaps they have examined us and decided contact is not worthwhile. Some scientists, like Carl Sagan, believed we should listen and search for signals. Projects like SETI scan the skies for radio transmissions, hoping to detect messages from distant worlds. Others argue that broadcasting our presence is reckless. What if contacted aliens are not friendly? What if revealing ourselves invites danger rather than discovery? Consider what finding life elsewhere would mean. Even microbial life on Mars or Europa would revolutionize understanding of biology. It would prove life is not unique to Earth, that the universe is fertile, that wherever conditions allow, life finds expression. But intelligent life? That would change everything. It would mean we are not alone in curiosity, not alone in searching for meaning. Somewhere across vast darkness, another species might be looking at their own sky, asking identical questions, wondering if anyone else exists. Whether we are alone or not remains unverified. Whether life is common or extraordinarily rare is unknown. Whether intelligent civilizations exist and why they have not made contact if they exist remains unexplained. The silence of the cosmos persists. Whether it indicates solitude or something else entirely is unresolved. Causes of mass extinctions. Mass extinctions have reshaped life on Earth repeatedly. Could we be experiencing the next one? Earth has undergone at least 5 mass extinctions, each eliminating most species and resetting evolutionary trajectories. The most famous, the asteroid that ended the dinosaurs. But while space rocks create dramatic endings, they are not the only suspect in Earth's greatest die-offs. Some theories suggest supervolcanoes played major roles. The Permian-Triassic extinction, often called the Great Dying, eliminated over 90% of marine species and 70% of land animals. The leading theory, Massive volcanic eruptions in what is now Siberia released so much carbon dioxide it triggered runaway global warming, rendering the planet nearly uninhabitable. Others point to climate shifts, not just warming, but cooling. The Ordovician-Silurian extinction witnessed an ice age suddenly sequester ocean water, devastating marine life. Then, when ice melted, sea levels surged, drowning coastal species. But some theories become more speculative. Could gamma-ray bursts, high-energy explosions from distant stars have stripped away Earth's ozone layer, exposing life to lethal radiation? Could dark matter passing through the solar system have subtly disrupted orbits, leading to devastating cosmic events? And then there is today. Many scientists argue we are in the middle of a sixth mass extinction, driven not by asteroids or volcanoes, but by human activity. Deforestation, pollution, climate change, pushing species to extinction at unprecedented rates. So what truly causes mass extinctions? Is it a single catastrophic event, or a slow, unavoidable cycle of planetary change? Consider the pattern of life itself. Every mass extinction creates opportunities. When dinosaurs vanished, mammals rose to dominance. When ancient marine ecosystems collapsed, new ones emerged. Death and rebirth. Destruction and creation. An endless cycle. Some extinctions happen rapidly, a single asteroid impact, a sudden volcanic eruption. Others unfold slowly, climate gradually shifting, ecosystems quietly collapsing, species disappearing one by one until the system can no longer sustain itself. But whether fast or slow, the result is identical: a world transformed, old species gone, new ones rising to fill the void. Whether we are in a sixth extinction now is debated. What comes after, if we are, remains unknown. What new forms of life might emerge from ruins left behind? What species, millions of years hence, will look back at our time as the great transition, the cycle of extinction and renewal continues? Whether current changes constitute mass extinction or normal fluctuation is disputed. What causes these planetary scale transformations remains incompletely understood. Punctuated equilibrium. What if evolution is not slow and steady but happens in sudden bursts? For decades, scientists believed evolution was gradual, tiny changes accumulating over millions of years. But in the 1,970 seconds, paleontologists Niles Eldredge and Stephen Jay Gould proposed something radical. Evolution does not always creep forward. It jumps. They called it punctuated equilibrium. Instead of gradual change, this theory suggests species stay mostly unchanged for long periods with little evolution occurring. Then suddenly a rapid burst of evolutionary change creates new species in a short geological time span. Think of it like a pressure cooker. Things remain stable for extended periods, but when the right conditions build up, transformation happens rapidly. Why is this idea controversial? Because it challenges the traditional Darwinian view of slow, continuous evolution. Some critics argue the fossil record simply is not complete enough, that gaps between species do not mean evolution happens in bursts, just that all transitional forms have not been found yet. Others worry that punctuated equilibrium oversimplifies evolution, downplaying natural selection's role over time. They point to examples of gradual change in the fossil record, showing not all evolution happens in leaps. But strong support exists for the idea. Fossil evidence shows many species appear suddenly in the geological record with little sign of gradual change. Some biologists believe this makes sense. Big evolutionary shifts could be triggered by environmental crises, genetic mutations, or sudden ecological opportunities. Consider the rhythm of life itself. If punctuated equilibrium is correct, evolution is not a smooth climb but a series of plateaus and sudden leaps. Long periods of stasis interrupted by brief moments of rapid transformation. Perhaps species remain stable because they are well adapted to their environments. Change is costly, risky. Most mutations are harmful, so populations resist change, maintaining identical forms for millions of years. But when the environment shifts dramatically, when climate changes or new predators arrive, old adaptations no longer function. Suddenly, change is not just possible but necessary, and evolution accelerates. This pattern appears not just in fossils but in living systems. Bacteria develop antibiotic resistance suddenly, not gradually. Invasive species explode in new environments, adapting rapidly to conditions their ancestors never faced. Whether evolution leaps or crawls remains debated. Whether both patterns occur under different circumstances is proposed. The pace of evolutionary change and what determines it remains incompletely understood. The debate between gradualism and punctuation continues without consensus. How evolution operates across different timescales and environmental contexts remains an active area of investigation. Role of sexual selection. Why do peacocks have elaborate tails? Why have some animals evolved traits that seem more burdensome than advantageous? According to Charles Darwin, it is because natural selection is not the only evolutionary force. There is another, sexual selection, and it has been shaping life on Earth as significantly as survival of the fittest. The idea is straightforward but powerful. Some traits do not make an animal better at surviving but do make them better at attracting mates. The peacock's tail useless for escaping predators but irresistible to peahens. The antlers of a stag not optimal for running through forests but essential for winning battles against rivals. In the world of sexual selection, the prize is not just survival but reproduction. But here is where controversy begins. Some scientists argue sexual selection explains far more than flashy feathers and courtship dances. It could be a driving force behind intelligence, creativity, even human behaviors like humor and artistic ability. Some researchers believe traits like music, storytelling, and abstract thinking evolved not because they helped hunt or gather food, but because they made individuals more attractive to potential mates. Art and culture are not just byproducts of large brains, they are the reason large brains evolved in the first place. Consider the bowerbird. Males spend weeks constructing elaborate structures, decorating them with colorful objects, shells, flowers, even bits of plastic, all to impress females. The structure serves no survival purpose. It is pure display, pure art. And females choose mates based on aesthetic preference. What if human creativity works similarly? What if music, stories, paintings are all evolutionary displays, signals of genetic fitness, displays of cognitive ability, ways of demonstrating what the brain can accomplish? However, not everyone accepts this idea. Critics argue sexual selection cannot fully explain why certain traits persist, especially when they seem impractical or costly. Others point out that in some species, mate choice does not follow simple patterns. Sometimes luck and circumstance matter more than biological traits. And then there is the question of symmetry. Why are symmetrical faces considered attractive across cultures? Some believe it signals genetic health, that asymmetry indicates developmental problems. But others argue this is cultural bias, that beauty standards are learned, not hardwired. Whether desire shaped intelligence and culture, or whether these emerged independently, remains debated. Whether sexual selection is as powerful as some claim or represents one factor among many is unresolved. What role attraction plays in shaping cognitive and cultural evolution remains uncertain. The debate continues across evolutionary biology, psychology, and anthropology. Classification of viruses. Are viruses alive? That question alone has fueled one of biology's biggest debates. Unlike bacteria or fungi, viruses do not eat, do not grow, do not breathe. But they do invade living cells, hijack their machinery, and replicate with ruthless efficiency. So, what exactly are they? And more importantly, how should they be classified? At first glance, viruses appear to be ultimate parasites, tiny genetic code wrapped in protein shells, incapable of independent function. They cannot reproduce without a host, which is why some scientists argue they are not even living organisms. Life, after all, is supposed to be self-sustaining. But complications arise. Viruses evolve. They mutate. They can even exchange genes with other organisms. That resembles life significantly. Scientists have attempted to sort viruses into neat biological categories, but there is a problem. They do not fit anywhere. The classical tree of life includes bacteria, archaea, and eukaryotes. Viruses lack a branch. Some propose a fourth domain of life, a separate category for viruses entirely. Others argue viruses might have once been cells that lost the ability to function independently, becoming genetic parasites over time, stripped down to bare minimum, just enough to invade, replicate, survive. Then there is another possibility. What if viruses preceded life as currently understood? Some theories suggest viruses may have been original genetic fragments that helped jumpstart evolution itself, floating in primordial soup, transferring genetic information between early cells, driving the first leaps in complexity. If true, that would mean viruses are not just strange biological parasites. They could be the missing link to understanding how life began. Consider what this means for the boundary between living and non-living. Life is assumed to be clearly defined: cells, metabolism, reproduction. But viruses blur that line. They exist in strange limbo, not quite alive, not quite dead, active only when inside a host, dormant when outside. Some viruses are enormous, larger than some bacteria, with genomes more complex than simple organisms. Others are tiny, just a handful of genes, barely more than molecular instructions. How does one classify something so diverse, so paradoxical? And then there is the question of their role in evolution. Viruses do not just cause disease, they transfer genes between species, driving genetic diversity. Some scientists believe viral DNA constitutes a significant portion of the human genome, that ancient viral infections left genetic remnants, fragments of code that became part of us. So, should the definition of life be revised? Or are viruses something else entirely, a biological anomaly that does not need to conform to standard categories? Whether viruses are living or non-living remains philosophically and scientifically contested. How to classify entities that defy traditional biological categories is unresolved. The nature of viruses and their place in the history of life remains debated. Role of epigenetics in evolution. What if your experiences could alter your children's biology? What if trauma endured, food consumed, even stress carried could be transmitted to future generations? For decades, evolution was understood as random mutations and survival of the fittest, a slow, generational process driven by DNA changes. But what if evolution is not just about genes? What if it is also about how those genes are expressed? This is the radical idea behind epigenetics, and it is rewriting what was thought known about evolution. Epigenetics does not change the genetic code itself. Instead, it acts like a dimmer switch, turning genes on or off based on environmental influences. Imagine two identical twins, same DNA, same blueprint. One experiences famine, the other does not. Years later, the twin who endured starvation might transmit altered gene expression to their children, making them more prone to storing fat. The DNA remains unchanged, but the way it is read and expressed differs. This idea is controversial because it challenges traditional Darwinian evolution. The standard model states evolution occurs through random mutations over millions of years. But epigenetics suggests organisms can adapt much faster within a single lifetime and pass those adaptations to offspring. Some scientists argue this is a modern update to Lamarck's theory, the idea that acquired traits can be inherited, which was largely dismissed for over a century. Lamarck proposed giraffes developed long necks because ancestors stretched to reach high leaves, and that this stretching was transmitted. Darwin's theory replaced this with natural selection, random mutations that favor longer necks. But epigenetics shows Lamarck might not have been entirely wrong. Studies demonstrate environmental factors like stress, diet, or trauma can cause chemical changes to DNA. These changes do not alter the genetic code itself but affect how genes are expressed, and these changes can be inherited for multiple generations. This has been observed in plants, animals, and humans. Children of Holocaust survivors show different stress hormone levels than peers. Descendants of famine victims have altered metabolism. Mice exposed to certain chemicals transmit anxiety-like behaviors to offspring, even though offspring were never exposed. Consider what this means for evolution. If experiences can shape biology, then organisms are not just passively waiting for random mutations. They are actively responding to their environment, and those responses can influence future generations. But critics remain skeptical. They argue epigenetic changes are temporary, lasting only a few generations before fading, that they do not drive long-term evolutionary change the way genetic mutations do. Others worry that calling this evolution dilutes the term's meaning, that short-term adaptation is being confused with true evolutionary change. Still, evidence continues mounting. Epigenetics is real. The question is how much it matters. Does it play a minor role in evolution? Or is it a major force that has been ignored? Whether epigenetics represents a significant evolutionary mechanism or a temporary adaptive response remains debated. How environmental experiences interact with genetic inheritance across generations is incompletely understood. Research continues without definitive conclusions about epigenetics' role in long-term evolutionary change. Nature of the vacuum. The vacuum of space, emptiness, nothingness, a vast sea of absolute void. But what if the vacuum is not empty at all? What if, instead of being dead silent abyss, space is teeming with energy, quantum fluctuations, virtual particles constantly appearing and disappearing? This is the mystery of the vacuum, and it is one of the most controversial questions in modern physics. In classical physics, a vacuum is simply the absence of matter, a place where no particles, no air, nothing exists. But quantum mechanics tells a different story. Even in the emptiest parts of the universe, space itself is alive with fleeting bursts of energy known as quantum fluctuations. These fluctuations create virtual particles, tiny entities that appear for fractions of seconds before disappearing. This is not just theoretical, it has been observed. The Casimir effect, for instance, shows empty space can exert force on objects. Vacuum energy, the so-called zero-point energy, is even thought to play a role in universe expansion. But this leads to a huge problem. If the vacuum is full of energy, why is not the universe collapsing under its own weight? The vacuum energy predicted by quantum mechanics is 120 orders of magnitude higher than what is observed. That number is so absurd it has been called the worst prediction in physics. So what is the vacuum really? Is it a quantum sea of infinite energy? A hidden layer of reality not yet understood? Or something even stranger? Consider what this means for the concept of nothingness. Empty space is thought of as ultimate absence, the place where nothing exists. But quantum mechanics suggests nothing is never truly empty. Even in the void, something is always happening. Particles appearing, disappearing, energy fluctuating. Some physicists believe the vacuum might hold the key to understanding dark energy, the mysterious force accelerating universe expansion. Perhaps the vacuum itself is pushing space apart. Perhaps its energy is what drives cosmic acceleration. Others speculate the vacuum might be connected to space-time's fabric itself. That empty space is not just a stage where physics happens, but an active participant shaping reality at the deepest level. Whether the vacuum is truly empty or filled with undetectable energy remains unresolved. What constitutes the fundamental state of space itself is unknown. The nature of nothingness and whether true emptiness exists anywhere in the universe is among physics' deepest questions. What fills the void, if anything, remains uncertain. Arrow of time. Time only moves forward. Aging occurs. The past is remembered but not the future. No matter how much desired otherwise, a broken egg never reassembles. But why? The fundamental laws of physics do not actually require time to have direction, so what forces time to march forward, never backward? This is the mystery of the arrow of time, one of the most puzzling questions in physics. At the core of this mystery is the second law of thermodynamics, which states entropy always increases. Entropy is a measure of disorder. The universe, it seems, is always moving toward more chaos. Ice melts, stars burn out, everything decays. This is the closest thing physics has to a rule giving time direction. The past is orderly. The future is messy. But there is a problem. The laws of physics work equally well in reverse. If atomic motion were filmed then played backward, it would still obey all known equations of motion. So why does not the universe behave this way on larger scales? Why are shattered glasses not observed reassembling, or spilled coffee leaping back into cups? One explanation is that the Big Bang established the universe in an extremely low entropy state, like a neatly stacked deck of cards. Over time, disorder has increased, creating the illusion of time flowing forward. But this raises another question. Why did the Big Bang start in such an ordered state to begin with? And could time ever run backward, under appropriate conditions? Some physicists speculate that in a distant contracting universe, time could reverse, creating a mirror reality where everything runs backward. If accurate, then time is not a fundamental force but just an effect of entropy. Consider what this means for memory and experience. The past is remembered because entropy was lower then, because order gradually dissolves into chaos. But the future cannot be remembered because it has not occurred yet, or has it? If time is just a direction determined by entropy, perhaps the future already exists. Access is simply unavailable. Perception is impossible because consciousness moves in one direction only. Whether time has objective direction or is merely perceived direction due to entropy remains philosophically and scientifically debated. Why time appears to flow forward, whether this is fundamental or emergent, and whether time travel backward is physically possible are unresolved questions. The arrow of time continues pointing forward. Whether this is necessity or contingency is unknown. Cosmological multiverse. What if the universe is not the only one? What if, beyond observable limits, there are countless other universes, each with its own galaxies, laws of physics, maybe even alternate versions of observers? This is the idea behind the cosmological multiverse, a theory suggesting our universe is just one of many, part of a vast, ever-expanding cosmic landscape. The idea stems from cosmic inflation, rapid expansion that occurred moments after the Big Bang. Some physicists, like Alan Guth and André Linde, proposed inflation did not just create our universe. It never stopped, continuing to spawn new universes perpetually. Each universe, or bubble, could have different physical constants, meaning the laws of nature taken for granted like gravity or electromagnetism might operate completely differently elsewhere. In some universes, stars might never form. In others, atoms might not hold together. In yet others, conditions might be perfect for life, perhaps more perfect than ours. But here is where controversy begins. There is no direct evidence. The multiverse is not something observable, measurable, or testable, which raises a huge question. Is it even science? Critics argue that without experimental proof, the multiverse is nothing more than philosophical speculation dressed in physics. Others counter that if inflation theory is correct and much of modern cosmology relies on it, then the multiverse is an unavoidable consequence, not a choice but a logical outcome of the equations. If true, it would change everything. It could explain why our universe seems so perfectly fine-tuned for life. Because in an infinite multiverse, there would naturally be some universes where conditions are just right. We exist in one of those, not because of design, but because we could not exist anywhere else. It is selection bias on a cosmic scale. But if these other realities can never be interacted with, does it matter? Some philosophers argue untestable theories are not science. That calling something real when it can never be observed stretches reality's definition itself. Others believe the multiverse is the most elegant solution to some of physics' deepest problems. Why are nature's constants so finely tuned? Why does our universe have the properties it does? The multiverse answers these questions without invoking design or coincidence. It simply states, all possibilities exist. We happen to inhabit one where life is possible. Whether the multiverse is real or mathematical possibility without physical instantiation remains among the most contested questions in contemporary cosmology. Whether universes beyond our own exist, and whether the concept belongs in physics or philosophy continues to be debated. What lies beyond the observable universe, if anything, remains unknown. Plate tectonics. The ground beneath observation is moving, not rapidly enough to perceive, but slowly, relentlessly, reshaping continents, raising mountains, opening oceans. This is plate tectonics, the unceasing motion of Earth's crust that explains why earthquakes shake cities, why volcanoes erupt, and why entire land masses drift apart over millions of years. But for extended periods, scientists dismissed this idea as implausible. Before the 20th century, continents were believed to be fixed in place, permanent features of the planet, unchanging. Then came Alfred Wegener, a German meteorologist who noticed something peculiar. The coastlines of South America and Africa fit together like puzzle pieces. He proposed that continents were not fixed at all but drifted across Earth's surface over time. His idea, called continental drift, was ridiculed. He had no explanation for how massive land masses could move. It simply did not seem possible. Decades later, under the ocean, geologists discovered mid-ocean ridges, huge underwater mountain chains, where new crust was forming. As molten rock rose from beneath, it pushed old crust away, slowly driving the continents apart. This discovery confirmed what Wegener had theorized all along. Earth's surface was not fixed. It was broken into giant plates, constantly shifting and colliding, but not everyone accepted it immediately. Some scientists argued that if plates are always moving, why is not Earth rupturing itself? Others questioned whether subduction, where one plate sinks beneath another, could actually recycle crust rapidly enough to balance the process. Even today, debates persist about what drives plate movement. Is it heat from Earth's core, or something even deeper? Consider what this means for landscape permanence. Mountains that appear eternal are temporary. Oceans that seem fixed will one day close. Continents that feel stable are slowly drifting. Nothing on Earth's surface is truly stationary. The Himalayas continue rising, a few millimeters each year as India pushes into Asia. The Atlantic Ocean widens as the Americas drift away from Europe and Africa. The Pacific shrinks as plates converge and subduct. Some scientists predict that in 200 million years, the continents will collide again, forming a new supercontinent, perhaps centered around the equator, perhaps at one of the poles. The exact configuration remains uncertain, but the movement continues. Whether plate tectonics operates on other planets is unknown. Whether Earth's geological activity is common or unusual in the solar system remains debated. What drives the convection currents that move plates is incompletely understood. The mechanisms underlying plate motion and the forces that have shaped Earth's surface for billions of years remain subjects of ongoing investigation. Origin of the Moon. The Moon hangs in the night sky, Earth's closest companion. But where did it actually come from? For something that has existed for over 4 billion years, its origin remains one of the most debated mysteries in science. For decades, scientists have attempted to piece together the Moon's origin story, but no single explanation fits perfectly. Some early theories suggested it simply formed alongside Earth from the same swirling cloud of dust and gas. Others argued that Earth captured the Moon, pulling in a wandering rock from space. The problem: neither fully explains why the Moon's composition is eerily similar to Earth's crust, yet missing certain elements. Then came the giant impact hypothesis, now the leading theory. According to this idea, around 4.5 billion years ago, a Mars-sized planet named Theia crashed into the young Earth. The collision was so violent that molten rock and debris were blasted into space, eventually coalescing to form the Moon. This explains why the Moon shares Earth's chemistry, but with key differences. Volatile elements were burned off in the fiery impact. But even this widely accepted theory has problems. Some scientists argue that if Theia truly existed, why have distinct chemical traces of it not been found? The Moon's composition is almost identical to Earth's mantle, too similar for a collision between two different bodies. Others suggest alternative ideas, the Moon forming from multiple smaller impacts, or even being spun out of Earth itself due to extreme rotation, a theory once favored but now largely dismissed. Consider what this means for Earth's past. If the giant impact happened, it was one of the most violent events in our planet's history. The collision would have vaporized rock, created a magma ocean covering Earth's surface. The debris ring that formed would have glowed in the sky, a molten halo slowly cooling and clumping together. Without that impact, Earth might be very different. The Moon stabilizes our axial tilt, giving us consistent seasons. It creates tides, which may have played a role in life's evolution, driving organisms from sea to land. Some researchers believe the Moon's formation was not just a cosmic accident, but a necessary step in making Earth habitable, that without Theia's collision, life as currently understood might never have emerged. No matter which theory proves correct, the Moon's origin is more than cosmic curiosity. It could hold the key to understanding Earth's past and even the formation of other planets. Whether the Moon resulted from impact, capture, co-formation, or another mechanism entirely remains incompletely resolved. How Earth acquired its satellite and what that reveals about planetary formation processes continues to be investigated. Mechanisms of photosynthesis. Without photosynthesis, life as currently understood would not exist. Every breath of oxygen, every bite of food, every towering tree all depend on this biological process that converts sunlight into energy. But there is a complication. The mechanism is still not fully understood. The basics are known. Plants take in carbon dioxide and water, use sunlight to trigger chemical reactions, and release oxygen while producing glucose. Simple enough. Not remotely. The molecular machinery inside plants is extraordinarily complex, operating with near-perfect efficiency, far beyond anything human engineers have constructed. And here is where real controversy begins. For years, scientists believed photosynthesis followed a straightforward step-by-step pathway. Light gets absorbed, energy gets transferred, chemical bonds get formed. But recent discoveries suggest quantum mechanics may be involved. Some studies indicate plant cells do not just transfer energy like a relay race. They may use quantum superposition to explore multiple pathways simultaneously, choosing the most efficient route. If true, this would mean plants have unknowingly been harnessing quantum physics for billions of years. Not everyone is convinced. Skeptics argue quantum effects are too delicate to survive in the messy, warm environment of a living cell. Others insist classical physics alone is sufficient to explain photosynthesis without requiring exotic quantum phenomena. The debate continues, with experiments pushing the limits of what was thought plants were capable of. Consider what this means for energy itself. Photosynthesis converts light into chemical energy with almost no waste. Solar panels, humanity's best technology, cannot approach this efficiency. Plants accomplish it effortlessly, every day, in every leaf, in every blade of grass. Some researchers are attempting to unlock this secret to create artificial leaves that could power entire cities. Imagine solar cells that work like chloroplasts, converting sunlight with the same efficiency as living plants. No batteries needed, no storage problems, just direct conversion from light to usable energy. But before reaching that point, one question remains. Have plants mastered physics in ways we are only beginning to understand? Whether quantum mechanics participates in photosynthesis or whether classical chemistry sufficiently explains the process remains contested. How plants achieve such remarkable energy conversion efficiency is incompletely understood. The molecular mechanisms underlying photosynthesis continue to be investigated across biophysics and biochemistry. Quantum effects in chemistry. Most assume chemistry is predictable. Two chemicals are mixed and they react. Simple. But what if some of the most important chemical reactions occur because of quantum physics? That at the tiniest scales, the molecular world is not as straightforward as assumed? This idea that quantum effects play a fundamental role in chemistry is both fascinating and controversial. Traditional chemistry operates on classical physics laws. It explains how atoms bond, how reactions occur, and how energy moves through molecules. But at extremely small scales, phenomena become anomalous. Particles do not behave like tiny billiard balls. They behave like waves, existing in multiple places simultaneously, tunneling through barriers they should not be able to cross, even choosing the most efficient reaction pathways as if they possessed foreknowledge of the best route. One of the most intriguing examples is enzyme catalysis, the process that accelerates chemical reactions inside bodies. Some researchers believe enzymes might be using quantum tunneling, a bizarre phenomenon where particles slip through energy barriers instead of climbing over them. If true, this means bodily chemistry relies on quantum tricks to function efficiently. And then there is photosynthesis. Some experiments suggest the way plants transfer energy might involve quantum coherence, where energy exists in multiple states simultaneously, finding the quickest route to the reaction center. If plants are secretly quantum physicists, what else in nature might be using these effects? Of course, skeptics argue that biological systems are too chaotic, too warm, for delicate quantum phenomena to survive. They believe classical physics alone can explain chemistry. But the more these effects are studied, the more evidence suggests nature might be playing by quantum rules in ways never imagined. If quantum mechanics is deeply embedded in chemistry, it could redefine understanding of everything from drug design to renewable energy. But the real question is, if life itself is quantum, what else is being missed? Whether quantum effects significantly influence chemical reactions in biological systems, or whether classical chemistry provides adequate explanation, remains debated. The boundary between quantum and classical behavior in molecular systems is incompletely defined. Research continues in quantum biology and chemical physics, without definitive conclusions. Nature of chemical bonding. What if the very mechanism holding the universe together, chemical bonds, is still not fully understood? By now, it would seem that exactly how atoms stick together should be known. Well, not quite. The nature of chemical bonding remains one of the most debated and mysterious topics in chemistry. At first glance, chemical bonds seem simple. Atoms share, steal, or swap electrons, forming stable molecules. This is standard education. Ionic bonds involve electron theft. Covalent bonds involve sharing. Metallic bonds create electron seas, case closed. Not exactly. Take covalent bonding, a fundamental concept. Traditional chemistry states atoms share electrons to form stable pairs, but quantum mechanics complicates this explanation. Electrons do not orbit like tiny planets. They exist in fuzzy probability clouds. In reality, when two atoms bond, their electrons do not just pair up straightforwardly. They enter a strange quantum superposition where they are distributed over both atoms simultaneously. So do molecules even have bonds in a classical sense? Or are they just complex quantum interactions? And then there is the mystery of the hydrogen bond. This weak attraction between molecules is responsible for everything from water's unique properties to DNA's structure. But is it even a bond at all? Some scientists argue it is more of an electrostatic force. Others believe quantum tunneling and entanglement may be involved. These questions are not merely theoretical. Understanding chemical bonding at deeper levels could revolutionize materials science, nanotechnology, even drug design. The problem: there is still no unified theory that fully explains all types of bonding in every situation. What if entire understanding of how matter holds together is incomplete? What else might be missing? Whether chemical bonds are best described by classical models, quantum mechanical frameworks, or some unified theory not yet developed remains debated. The fundamental nature of atomic interactions and what constitutes a chemical bond philosophically and physically continues to be investigated across theoretical and experimental chemistry. Mechanisms of atmospheric chemistry. Earth's atmosphere is a vast, swirling chemical laboratory, constantly reacting, shifting, reshaping the conditions that make life possible. But despite deep understanding of chemistry, one thing scientists still debate is: how exactly do the countless chemical reactions in the atmosphere work, and what forces are shaping them? At first glance, atmospheric chemistry seems straightforward. Sunlight breaks molecules apart. Oxygen reacts with pollutants. Weather moves everything around. But when examined closely, phenomena become anomalous. The air is filled with radicals, highly reactive molecules that exist for mere fractions of seconds before disappearing into new compounds. Some of these reactions create the ozone layer, shielding from deadly radiation. Others form acid rain, corroding cities and forests. And some, like the interplay of carbon dioxide, methane, and aerosols, determine Earth's climate itself. One of the biggest debates in atmospheric chemistry concerns how human activity influences these reactions. Emissions from factories and cars change air quality, that much is known. But predicting exactly how new chemicals will interact in the atmosphere is challenging. For instance, scientists once thought CFC's chlorofluorocarbons were harmless until they were discovered destroying the ozone layer. What other invisible dangers are being missed? Then there is the mystery of climate feedback loops. Do certain atmospheric reactions amplify warming or help cool the planet? And how much do natural processes like volcanic eruptions or plant emissions contribute compared to human-made pollutants? Consider the hydroxyl radical, often called the atmosphere's detergent. This molecule cleans the air by breaking down pollutants, but its concentration varies wildly depending on sunlight, humidity, and other factors. If hydroxyl levels drop, pollutants linger longer. If they rise, the air cleans itself faster. These changes can be measured, but predicting them remains difficult. Some researchers are exploring whether atmospheric chemistry can be manipulated intentionally. Geoengineering proposals suggest injecting particles into the stratosphere to reflect sunlight, cooling the planet artificially. But this comes with unpredictable risks. What if unintended reactions are triggered? What if weather patterns are disrupted? What if the cure is worse than the disease? If atmospheric chemistry could be fully decoded, methods might be found to engineer cleaner air, prevent climate disasters, or even terraform other planets. But until then, the air around us remains an unpredictable, ever-changing puzzle, one still being raced to solve. How atmospheric chemistry responds to natural and anthropogenic perturbations is incompletely modeled. The complex interactions between radiation, chemical species, and climate systems remain subjects of ongoing research. Whether large-scale atmospheric modification is feasible or advisable continues to be debated. Existence of quasicrystals. Crystals are supposed to follow rules perfectly, repeating patterns of atoms forming precise structures. But what if nature had been hiding a completely different kind of order? Something that defied everything thought known about solid matter? This is the strange world of quasicrystals, materials that should not exist, yet somehow do. For decades, scientists believed all crystals had translational symmetry, meaning their atomic structures repeated predictably, like tiles on a bathroom floor. But in 1982, Israeli scientist Dan Shechtman discovered something that shattered this assumption. He found a material with an ordered atomic structure that never repeated, arranged in a way that was mathematically impossible. Or so everyone thought. The discovery was met with ridicule. Crystallography textbooks stated with certainty that quasicrystals could not exist. Shechtman was even laughed at by colleagues and told to read a book on solid-state physics. For years, the scientific community rejected his findings. But as more researchers examined the evidence, they realized Shechtman was correct. In 2011, he won the Nobel Prize in Chemistry for proving quasicrystals were real. So why is this so controversial? Because it rewrote fundamental understanding of solid matter. Quasicrystals challenge the traditional definition of what a crystal even is. They also appear in unexpected places. Some have been found in meteorites, hinting that nature may have created them long before humans did. Now, scientists are exploring how quasicrystals could be used in everything from non-stick coatings to ultra-hard materials. Their unique structure gives them properties that ordinary crystals lack. They are harder, more resistant to heat, and they interact with light in unusual ways. But their existence still raises deeper questions. Are there other unknown forms of matter waiting to be discovered? What other impossible structures might nature be hiding? Whether quasicrystals represent a distinct state of matter or an exotic variation of crystalline order continues to be investigated. What other atomic arrangements are possible, and whether additional forms of ordered matter exist beyond current classification schemes remains uncertain. The discovery of quasicrystals has expanded understanding of how atoms can organize, but what limits exist on possible material structures is unknown. Molecular machines. Imagine machines so small they could fit inside a single cell, repairing DNA, delivering drugs directly to diseased tissues, or even assembling molecules with atomic precision. These are not science fiction. They are molecular machines, and they could revolutionize medicine, technology, and even how life itself is conceptualized. Molecular machines are nanoscale structures that move, rotate, and perform mechanical tasks, just like gears and levers in a watch, except operating at the scale of individual molecules. Some already exist in nature. Take ATP synthase, an enzyme found in cells that spins like a microscopic turbine to produce energy, or kinesin proteins, which literally walk along cellular highways, carrying vital cargo step by step with remarkable precision. But what if custom molecular machines could be designed and built? Scientists are now developing synthetic versions, tiny molecular motors that can be controlled by light, electricity, or chemical reactions. In 2016, this work won the Nobel Prize in Chemistry, marking a huge leap toward a world where artificial molecular machines could be used for everything from targeted drug delivery to creating self-repairing materials. So why is this controversial? Because if molecular machines can be engineered, could self-replicating ones one day be created? The idea of nanobots multiplying uncontrollably inside the body or environment sparks both excitement and fear. Some researchers worry about unintended consequences. Others argue such scenarios are still far from reality. But one thing is certain: molecular machines have already begun blurring the lines between biology and technology. Consider what this means for medicine's future. Imagine a molecular machine that could travel through bloodstreams, seeking out cancer cells, delivering chemotherapy directly to tumors, sparing healthy tissue. Or a machine that could repair damaged DNA, preventing genetic diseases before they manifest. Some researchers are exploring molecular machines that could clean up pollution, breaking down plastic waste at the molecular level. Others are designing machines that could build materials from the ground up, atom by atom, creating substances with properties never seen. But the real question remains: could a fully synthetic life form one day be built from scratch? If nature has spent billions of years perfecting molecular machines, how long will it take to catch up? Whether molecular machines will transform technology and medicine or remain primarily tools for specialized applications is uncertain. The technical challenges of designing, controlling, and deploying molecular-scale devices in complex environments remain substantial. Research continues across chemistry, biology, and nanotechnology without complete understanding of what is ultimately achievable at molecular scales. Role of volcanism in climate. There is a force on Earth that has shaped entire continents, wiped out species, and even altered the course of human history, all without conscious intention. Volcanoes. They are not just fiery mountains. They might be one of the most powerful climate influences on the planet. Some scientists even argue volcanic eruptions have played a bigger role in shaping Earth's climate than previously realized. Volcanoes release massive amounts of gases and particles into the atmosphere. Some, like carbon dioxide, trap heat and contribute to global warming. Others, like sulfur dioxide, reflect sunlight and cause cooling. A single large eruption can lower global temperatures for years. The 1,815 eruption of Mount Tambora in Indonesia was so massive it triggered the year without a summer, plunging temperatures, ruining crops, and leading to widespread famine. Snow fell in summer. People starved. All because one volcano exploded. But here is where controversy begins. Some researchers believe volcanic activity has contributed to long-term climate change, even playing a role in past ice ages. Others argue that while individual eruptions can cause short-term cooling, their impact is insignificant compared to human-driven carbon emissions. The biggest debate: whether modern climate change models properly account for volcanic influences. Some claim they overestimate the role of carbon dioxide while underestimating volcanic effects. Consider what this means for Earth's climate history. Every major volcanic event has left its mark. The Deccan Traps in India, the Siberian Traps, massive volcanic provinces that erupted for thousands of years, releasing enough gas to alter global temperatures, trigger mass extinctions, reshape ecosystems. Some scientists believe these ancient eruptions were more influential than asteroid impacts. That volcanic activity drove climate shifts that made life impossible for countless species. That the slow, relentless release of gases was more deadly than any single cosmic collision. If volcanoes have altered climate before, could they do it again? And more importantly, could this natural force one day be harnessed, perhaps even trigger small eruptions to cool the planet intentionally? A speculative idea, but considering how much power volcanoes already possess, maybe nature has been running its own climate experiments all along. Whether volcanic forcing significantly affects long-term climate trends or primarily produces short-term perturbations remains debated. How volcanic emissions compare to anthropogenic contributions in contemporary climate change, and whether volcanic activity could be intentionally manipulated for climate intervention, are questions without consensus. The role of volcanism in Earth's climate system continues to be investigated across geology, atmospheric science, and climatology. Future of ice sheets. The fate of the world's ice sheets could determine civilization's future. These vast frozen landscapes hold enough water to reshape coastlines, inundate cities, and alter global weather patterns in ways only beginning to be understood. But how much ice will melt, and how rapidly, remains one of the most controversial questions in climate science. Greenland and Antarctica contain 2/3 of the planet's fresh water, locked away as ice. If they were to melt completely, sea levels could rise by over 200 feet, transforming major cities into underwater relics. But that is not the only concern. As ice sheets break apart, they disrupt ocean currents, affect weather systems, and even influence Earth's rotation. The real debate lies in how quickly this process is unfolding. Some scientists argue the tipping point has already been passed, with irreversible melting underway. The evidence, the collapse of ice shelves in Antarctica, the accelerating flow of glaciers, and the discovery that warming water is eroding ice from below. Others believe there is still time, that ice sheets are more resilient than assumed, and that stabilizing global temperatures could slow or even halt their retreat. But here is the real question. What happens if projections are incorrect? If ice loss is faster than predicted, catastrophic flooding could occur within current lifetimes, coastal cities evacuated, entire nations displaced, infrastructure destroyed. The economic and human cost would be staggering. Consider what this means for the future. Miami, New York, London, Shanghai, all vulnerable, all at risk. Some projections suggest that within a century, these cities could be fighting a losing battle against rising seas, building walls, pumping water, retreating inland. Some researchers are exploring radical solutions. Could the poles be refrozen, ocean currents redirected, water pumped onto ice sheets to slow their slide into the sea? These ideas sound speculative, but as ice continues melting, desperation breeds innovation. Then there is the question of adaptation versus prevention. Should focus be on reducing emissions to stop the melting, or accept that some loss is inevitable and prepare for a world with higher seas? The controversy is not just scientific, it is political, economic, ethical. Who pays for the damage? Who decides which cities to save? Who gets displaced? And where do they go? Whether ice sheet collapse is imminent, gradual, or potentially reversible remains uncertain. How societies should respond to potential sea level rise and whether technological interventions could meaningfully affect ice sheet dynamics are questions without clear answers. Research continues across glaciology, oceanography, and climate science, but projections carry substantial uncertainty ranges. Possibility of a supercontinent. Earth's continents are drifting. But where are they going? Right now, continents are scattered across the globe, but geologists believe they are slowly moving toward a future supercontinent, one that could reshape life on Earth in ways barely imaginable. This is not speculation, it has happened before. Hundreds of millions of years ago, all land on Earth was fused together in a massive supercontinent called Pangaea. Over time, it broke apart, creating the continents recognized today. But plate tectonics never stops. Continents are constantly shifting, moving at approximately the same speed as fingernails grow. And in another 200 to 300 million years, they could collide again, forming a new supercontinent. There are several competing models for what this might resemble. One idea, called Pangaea Proxima, suggests continents could slowly drift back together into one massive landmass near the equator. Another, called Amasia, predicts North America and Asia could merge at the North Pole. Meanwhile, the Novo Pangaea model envisions a completely new land arrangement driven by changes in ocean currents and plate motion. But what would this mean for life on Earth? A supercontinent could drastically alter climate patterns, potentially creating vast deserts or extreme weather zones. It could also disrupt ocean currents, reshaping ecosystems and possibly triggering mass extinctions. Consider what happened to Pangaea. Its interior was a scorching desert, too far from the ocean to receive rain. Life concentrated along coasts where water and moderate temperatures existed. The center was barren, hostile, uninhabitable. If another supercontinent forms, similar patterns could emerge: massive inland regions devoid of life, coastlines teeming with biodiversity, weather systems unlike anything currently observed, monsoons of unprecedented intensity, droughts lasting centuries. Some scientists argue predicting plate tectonics millions of years into the future is impossible due to the chaotic nature of the process. Others believe the models are solid, based on how continents have behaved in the past. But here is the deeper question. If Earth is heading toward another supercontinent, what will the world look like? Will it be a paradise of connected land masses, or a hostile environment of extreme conditions? And if humans are still present, will adaptation occur, or will another home need to be found? Whether another supercontinent will form, and what configuration it might take, remains speculative. Plate tectonic models extend hundreds of millions of years into the future, but uncertainties compound over such timescales. How continental assembly would affect global climate, ocean circulation, and biological evolution is incompletely understood. The future geography of Earth remains a subject of geological modeling without empirical verification. Causes of earthquakes. The ground beneath observation is not as solid as it seems. In an instant, Earth can shake violently, tearing apart cities, triggering tsunamis, reshaping landscapes. But what actually causes earthquakes? And why do some scientists believe there is more to them than just shifting tectonic plates? The most widely accepted explanation is plate tectonics. Earth's crust is not a single solid shell, but broken into massive pieces called tectonic plates that float on a layer of molten rock. As these plates move, they grind against each other, get stuck, and build up stress. When that stress finally releases, the result is an earthquake. Simple. Or so it seems. Not always. Some researchers argue not all earthquakes fit neatly into this model. For example, deep earthquakes, those occurring more than 300 miles below the surface, happen in areas where rocks should be too hot and soft to store enough stress to rupture. Scientists suspect other forces may be at play, such as mineral transformations that release energy deep within the mantle. Then there is the theory that earthquakes might not always be natural. Human activity, such as fracking, dam construction, and deep mining, has been linked to unexpected seismic activity. Some earthquakes have even occurred in places where tectonic movement is not common. Could human actions be creating artificial fault lines? And here is where things get even more speculative. Some researchers wonder whether electromagnetic shifts or even solar activity might have subtle influences on earthquake patterns. While mainstream geology does not fully embrace these ideas, they continue to be explored. Consider what this means for prediction. If earthquakes are purely mechanical, driven by plate stress, then monitoring strain buildup should enable prediction. But despite decades of research, reliable earthquake prediction remains elusive. Seismologists can identify high-risk zones, but pinpointing when a quake will strike remains nearly impossible. Some scientists believe Earth's crust is simply too complex, too chaotic, that tiny changes in pressure, temperature, or fluid movement can trigger massive ruptures, making prediction fundamentally impossible. Others argue something is being missed, that hidden factors beneath the surface influence when and where earthquakes occur, forces not yet discovered. So are earthquakes simply the product of grinding plates? Or is there more to the story? If the planet is constantly shifting, what unknown forces might still be waiting to shake up understanding of how Earth really works? What triggers individual seismic events and whether earthquakes can ever be reliably predicted remains unresolved. The mechanics of deep earthquakes, the role of fluids in fault activation, and potential anthropogenic contributions to seismicity continue to be investigated. Whether electromagnetic or astronomical factors play any role in earthquake timing is highly contested with minimal supporting evidence. Seismology continues developing better monitoring and early warning systems, but prediction remains elusive. Mechanisms of mountain formation. Mountains are Earth's greatest sculptures, but how exactly are they formed? Most assume mountains have always been present, standing tall and immovable, but in reality they are dynamic, constantly growing, eroding, even vanishing over millions of years. The real question is, what forces are powerful enough to push entire landscapes miles into the sky? The standard explanation ties mountain formation to plate tectonics. When massive sections of Earth's crust tectonic plates collide, the land has nowhere to go but upward, creating enormous mountain ranges like the Himalayas. The collision between the Indian and Eurasian plates, for example, continues to push Mount Everest higher by a few millimeters each year. But is this the complete story? Some scientists argue mountains do not just form from plate collisions. Some may rise due to forces from deep within Earth. Mantle plumes, rising columns of superheated rock could be responsible for uplifting vast regions. Others suggest intense erosion and climate changes may contribute, reshaping landscapes in ways not fully understood. Then there is the debate over ancient mountain ranges. If plate tectonics explain modern mountains, why is evidence of ancient mountain belts found in places where no major tectonic activity exists today? Could missing geological processes be at play? Consider the Appalachian Mountains. Once as tall as the Himalayas, now worn down to gentle hills, they formed hundreds of millions of years ago when continents collided. But their story reveals something deeper. Mountains are not permanent. They rise, they fall, they disappear entirely, only to be replaced by new ranges in different locations. Some researchers believe the balance between uplift and erosion determines a mountain's fate. If uplift is faster, mountains grow taller. If erosion is faster, they shrink. But this balance is delicate, influenced by climate, rainfall, temperature, even the types of rocks involved. And then there is the mystery of how quickly mountains can form. Some ranges seem to have risen in geological instants, others took tens of millions of years. What determines the speed? Is it the force of collision, the angle of impact, the composition of the crust? Mountains hold the history of Earth's violent past, and yet their formation is still full of mysteries. Are hidden forces shaping the land beneath us? Or are all answers available, just requiring deeper investigation? Perhaps beneath observation, the planet is still deciding where the next great mountain range will rise. What controls the rate of mountain building? Why some regions undergo rapid uplift while others change slowly, and how erosion interacts with tectonic processes to shape topography are incompletely understood. The relative contributions of different uplift mechanisms, collision, subduction, mantle dynamics, isostatic adjustment vary by location and remain subjects of geological investigation. Mountain formation involves complex interactions between tectonic forces, surface processes, and material properties that are still being characterized. Role of asteroids in Earth's history. What if Earth's history was shaped not by slow, gradual changes, but by sudden cataclysmic impacts from space? Asteroids, those wandering space rocks, have a reputation for destruction, but their role in shaping the planet might be far greater than ever imagined. Some scientists argue that without them, life as currently understood would not even exist. The most famous example, the Chicxulub impact, the asteroid that wiped out the dinosaurs 66 million years ago. When this 6-mile-wide rock slammed into what is now Mexico's Yucatan Peninsula, it unleashed destruction on a planetary scale. Shock waves, wildfires, tsunamis, and a cloud of debris that plunged Earth into darkness. Without that impact, mammals our ancestors might never have taken over. But that is just one theory. Some researchers believe asteroids did not just wipe species out, they may have also helped create life. Early Earth was bombarded by space debris, and some scientists think these impacts may have delivered water, organic molecules, and even the building blocks of life itself. If true, then the very event that nearly wiped out life millions of years ago could be the same force that made it possible in the first place. Not everyone agrees. Some argue Earth's geology and volcanic activity played a bigger role in extinctions and climate changes than asteroid impacts ever did. Others suggest asteroid-delivered organic molecules were unnecessary, life could have emerged from Earth's own chemistry. So which is it? Are asteroids cosmic harbingers of doom, or essential ingredients for life's creation? Consider the evidence scattered across Earth's surface: impact craters, some enormous, some barely visible, each one a reminder that the planet has been struck repeatedly throughout its history. The Vredefort crater in South Africa, the Sudbury Basin in Canada, the Barringer crater in Arizona, all testament to violent collisions. Some scientists believe these impacts did more than just create craters. They may have triggered volcanic eruptions, altered ocean chemistry, released greenhouse gases, reshaped continents, each collision a reset button, forcing evolution down new paths. And then there is the unsettling question: if another impact were headed this way today, would it mark the end or the beginning of something new? NASA and other space agencies are tracking thousands of near-Earth objects, monitoring their orbits, calculating collision probabilities. But space is vast, and asteroids are small. What if one slips through undetected? Whether asteroids were primarily destructive or constructive forces in Earth's history remains debated. How frequently large impacts have occurred, what their long-term effects on climate and evolution have been, and whether impact delivery of organic molecules was necessary for life's origin are questions without definitive answers. The relative importance of impacts versus other geological and biological processes in shaping Earth's history continues to be investigated. Asteroid detection and deflection capabilities are advancing, but whether civilization could successfully prevent a catastrophic impact remains untested. Origin of the elements. Everything around observation, the air breathed, water consumed, even the body itself is made from a collection of elements. But where did those elements come from? Why does the universe have hydrogen, carbon, gold, and uranium instead of nothing at all? The answer is buried deep in the hearts of stars, supernovae, and the very fabric of the cosmos itself. Scientists believe elements were forged in a sequence of violent, universe-shaping events. The lightest elements, hydrogen and helium, were born moments after the Big Bang, but the heavier ones, the oxygen in lungs, the iron in blood, the gold in jewelry, they came from something far more extreme: the death of stars. Inside the cores of massive stars, atoms smash together, fusing into heavier elements. When those stars explode as supernovae, they scatter these elements across space, seeding the universe with the building blocks of planets, life, and everything recognized. But not everyone agrees on the exact details. Some physicists argue neutron-star collisions, not just supernovae, played a key role in producing the heaviest elements like gold and platinum. Others suggest the conditions for element formation might have been different in the early universe than currently assumed. Could unknown physics have shaped the periodic table in ways still not understood? This mystery is far from settled, and new discoveries keep challenging assumptions. Consider what this means for existence. Every atom in the body was forged in the heart of a dying star, literally composed of stardust. The calcium in bones, the iron in blood, the carbon in DNA, all created billions of years ago in stellar furnaces, then scattered across space, eventually coalescing into planets, into life, into individual observers. Some researchers believe entirely different cosmic processes produce elements not even considered. What if black holes play a role? What if dark matter interactions influence element formation? What if the early universe had conditions that cannot be replicated? The periodic table is the cosmic recipe book, but exactly how the universe wrote it is still being determined. Whether all element formation pathways are understood, what processes created the heaviest elements, and whether nucleosynthesis occurred differently in the early universe than it does in contemporary stars remains uncertain. The relative contributions of different astrophysical sites, core collapse supernovae, type Ia supernovae, neutron star mergers, massive star winds to the chemical enrichment of the universe continue to be quantified. Element formation remains an active area of nuclear astrophysics with ongoing revisions to theoretical models. Origin of the cosmic microwave background. There is an invisible whisper from the birth of the universe, stretching across the entire cosmos. A faint, persistent signal that exists everywhere, all the time. It is not coming from stars, black holes, or galaxies. It is coming from the very beginning of time itself. This is the cosmic microwave background, the CMB, and it might be the most important clue about the origins of the universe. The CMB is often described as the afterglow of the Big Bang, the remnant heat from a time when the universe was just a hot, dense soup of particles. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form, allowing light to travel freely for the first time. That light has been stretching and cooling ever since, eventually becoming the faint microwave radiation detected today. This discovery was transformative. In 1964, scientists Arno Penzias and Robert Wilson accidentally stumbled upon this signal while trying to eliminate interference from their radio telescope. Instead of noise, they had uncovered the oldest light in the universe, confirming key predictions of the Big Bang model. But here is where things become controversial. While most cosmologists accept the CMB as definitive evidence of the Big Bang, some dissenters argue alternative theories could explain the data differently, the steady-state theory or cyclic universe models. Others debate whether unexplained anomalies in the CMB, like the so-called cold spot, hint at new physics or even parallel universes. Consider what this signal represents. When a television is tuned to static between channels, a tiny fraction of that noise is actually the cosmic microwave background. The echo of creation itself is being observed, the universe's oldest light filling every corner of space. Some researchers study the CMB's temperature fluctuations, tiny variations that reveal how matter clumped together in the early universe. These fluctuations eventually became galaxies, stars, planets, everything observed today. The seeds of structure, frozen into radiation, preserved for billions of years. But mysteries remain. Why is the CMB so uniform? Why does it have the exact temperature it does? And what do the anomalies mean? Some scientists believe these irregularities point to collisions with other universes. Others think they are simply statistical flukes, meaningless noise in the data. So, is the cosmic microwave background final proof of the Big Bang? Or is it hiding something even more profound? If this is the universe's oldest signal, what else could it be revealing about reality itself? Whether the CMB contains signatures of pre-Big Bang physics, whether observed anomalies indicate new cosmological phenomena or are statistical artifacts, and what fine-scale structure in the CMB reveals about early universe conditions remains subjects of ongoing investigation. The cosmic microwave background is the most precisely measured relic of the early universe, yet questions about its detailed interpretation persist. Cosmology continues refining measurements and theoretical models to extract maximum information from this primordial signal. Existence of a molten core. Beneath observation, just a few thousand kilometers down, lies a world of molten rock and searing metal, a vast, churning ocean of liquid iron that keeps the planet alive. At least, that is what most scientists believe. The existence of Earth's molten core is one of the most widely accepted ideas in geology. But here is the complication. No one has ever seen it. Unlike the surface of the moon or even the depths of the ocean, drilling has never reached deep enough to directly observe the core. The deepest hole ever drilled, the Kola Super Deep borehole, only scratched about 12 kilometers down, just 0.2% of the way to the center. Everything known about Earth's interior comes from indirect clues: seismic waves, magnetic fields, and computer models. Seismic data provides the strongest evidence. When earthquakes happen, they send shock waves rippling through the planet. Some waves can pass through liquid while others cannot, creating a pattern suggesting a solid inner core surrounded by a molten outer core. This dynamic system is believed to generate Earth's magnetic field, shielding from deadly cosmic radiation. Without it, life as currently understood would not exist. But not everyone is convinced. Some alternative theories propose Earth's core might not be as molten as assumed, or that different materials, perhaps even exotic unknown substances, exist deep inside. Others question whether how Earth's magnetic field is generated is fully understood, suggesting new discoveries could rewrite what is thought known. Consider what this means for understanding of the planet. Existence on a thin crust floating on a sea of molten rock, powered by a core never touched, never measured directly, never truly observed. The entire model of Earth's interior is built on inference, on waves passing through darkness, on magnetic fields detected but not explained. Some researchers believe the core is more complex than a simple ball of molten iron. Perhaps it contains hidden layers. Perhaps it rotates at different speeds than the surface. Perhaps it holds secrets about Earth's formation, about how planets form their centers. And then there is the mystery of Earth's magnetic field itself. It flips, reverses polarity. North becomes south, south becomes north. This has happened many times throughout history. But why is not fully understood, or when it will happen again. If Earth's core is more complex than imagined, what else might be hidden beneath the surface? Is the planet's heart still a mystery waiting to be unraveled, or has the answer been observed all along? Whether Earth's core composition, structure, and dynamics are fully characterized remains uncertain. How the geodynamo operates to generate the magnetic field, what causes geomagnetic reversals, and whether the inner core rotates differentially from the mantle are questions with competing models. The core-mantle boundary and its influence on mantle convection and surface geology is incompletely understood. Direct observation remains impossible with current technology, so models rely on seismology, geomagnetism, and theoretical physics. Core dynamics continue to be investigated across geophysics and planetary science. Gaia hypothesis. What if Earth is not just a planet but a living, self-regulating organism? This is the Gaia hypothesis, the idea that life does not just exist on Earth but shapes it, creating feedback loops that maintain conditions necessary for life itself. At first, this sounds almost mystical, but it is a serious scientific proposal, one that challenges how the relationship with the planet is perceived. First introduced by James Lovelock in the 1970 seconds, the Gaia hypothesis suggests Earth's atmosphere, oceans, and ecosystems work together like a vast, self-regulating system. Take oxygen, for example. It makes up about 21% of air, perfect for life. Too much more, and fires would rage uncontrollably. Too much less, and complex life would not survive. So why has this delicate balance remained stable for millions of years, despite natural disasters, asteroid impacts, and climate shifts? According to the Gaia hypothesis, life itself adjusts conditions to keep the planet habitable. This idea sparked intense debate. Some scientists saw it as poetic metaphor rather than testable theory. Others embraced it as a radical way to rethink Earth systems. Critics argue natural selection does not work at planetary scales. Organisms evolve to survive, but the planet itself is not alive in any scientific sense. Others counter that Gaia's feedback loops are real, seen in how forests regulate rainfall or how plankton influence cloud formation. Consider the carbon cycle. Plants absorb carbon dioxide, animals release it, oceans store it, volcanoes release it. The system balances itself over geological time, not perfectly, not instantly, but persistently, as if the planet is maintaining equilibrium. Some researchers point to Earth's temperature stability. Despite the sun growing hotter over billions of years, Earth's surface temperature has remained relatively constant. How? Through atmospheric regulation, cloud formation, ice sheet dynamics, biological processes that respond to change. But Gaia is not a benevolent guardian. The hypothesis does not suggest Earth protects life out of kindness. It simply describes how life and environment co-evolve, shaping each other, sometimes catastrophically. If the Gaia hypothesis is correct, it means Earth is not just a passive rock floating in space. It is an active participant in the evolution of life, a planet that breathes, adjusts, responds. But if these delicate feedback loops are disrupted too much, could Earth stop working in favor of current life forms? Some scientists warn human activity is overwhelming Gaia's regulatory capacity, pushing the system beyond its ability to self-correct. Others believe the planet will adapt, finding new equilibrium with or without humanity. And if planets can regulate themselves, could life be shaping other worlds across the universe? Whether Earth functions as an integrated self-regulating system, or whether observed feedbacks are coincidental rather than homeostatic remains philosophically and scientifically contested. The Gaia hypothesis has evolved from its initial formulation into various testable models about biogeochemical cycling and climate regulation. Whether life actively maintains planetary habitability or merely responds to changing conditions continues to be debated across Earth system science, ecology, and biogeochemistry. The extent to which biological processes influence global conditions versus being influenced by them remains an active research question. Lamarckian evolution. What if giraffes did not evolve long necks because of random mutations, but because their ancestors stretched their necks higher and passed that ability down? This idea, Lamarckian evolution, was once laughed out of biology, but today it is making a surprising comeback. Proposed by Jean-Baptiste Lamarck in the early 1800s, this theory suggested organisms could pass on traits acquired during their lifetime. A blacksmith's son, for example, might inherit stronger muscles because his father spent years working metal. This idea made intuitive sense at the time, but then Darwin's theory of natural selection came along, arguing evolution happens through random genetic mutations, not because an organism wants or needs to change. Eventually, Mendelian genetics proved DNA does not work the way Lamarck thought. and his theory was dismissed as an outdated relic. But here is where things get anomalous. Recent discoveries in epigenetics suggest Lamarck might not have been entirely wrong. Studies show environmental factors like stress, diet, or trauma can cause chemical changes to DNA that affect how genes are expressed. These changes do not alter the genetic code itself, but can be inherited for multiple generations. This has been observed in plants, animals, and humans, suggesting life experiences might, in a way, shape future generations. Does this mean Lamarckian evolution was correct all along? Not exactly. Natural selection remains the dominant force in evolution, but epigenetics proves traits can sometimes be passed down in ways Darwin never imagined. So is evolution purely random? Or do organisms influence their own future in ways only beginning to be understood? Whether acquired characteristics can be inherited through epigenetic mechanisms, how long such inheritance persists, and whether it constitutes evolution in the Darwinian sense remains debated. Epigenetic inheritance has been demonstrated, but its role in long-term evolutionary change versus short-term adaptation is unclear. Whether epigenetic modifications provide raw material for natural selection or represent a distinct inheritance system continues to be investigated. The mechanisms, prevalence, and evolutionary significance of transgenerational epigenetic effects remain active areas of research across genetics, developmental biology, and evolutionary theory. Quantum coherence in biology. What if some of life's deepest mysteries, like how birds migrate, how brains process thoughts, or even how plants capture sunlight, are not just biology but quantum physics at work? This is the strange and controversial idea behind quantum coherence in biology, a theory suggesting living systems might harness the bizarre effects of quantum mechanics to function in ways not yet fully understood. Quantum coherence is when particles like electrons or photons exist in superposition, essentially being in multiple states simultaneously. In normal conditions, this effect is fragile and quickly collapses in messy, warm environments. But somehow, life seems to have found a way to use it. One of the strongest pieces of evidence: photosynthesis. Plants absorb sunlight and convert it into energy with near-perfect efficiency. Scientists discovered that instead of light energy taking a random, inefficient path through plant cells, it appears to explore multiple routes simultaneously, just like a quantum wave, before choosing the fastest one. This should not be possible in biological systems, and yet it happens. Another case: bird navigation. Some researchers believe migratory birds like robins use quantum entanglement in their eyes to see Earth's magnetic fields, helping them navigate across continents with astonishing precision. If true, this would mean evolution has somehow tapped into quantum mechanics, something struggled with even in controlled lab environments. But here is the controversy. Many scientists remain skeptical, arguing quantum effects are simply too delicate to survive in biological conditions. They believe classical physics alone can explain chemistry. But the more these effects are studied, the more evidence suggests nature might be playing by quantum rules in ways never imagined. Consider what this means for life itself. If quantum biology is real, then the processes keeping organisms alive, thoughts in brains, energy in cells, might all depend on quantum phenomena. Not just chemistry, not just biology, but something deeper, something at the edge of physics, Some researchers are exploring whether quantum coherence plays a role in consciousness itself, whether brains use quantum effects to process information, to create awareness, to generate thought. If true, it would blur the line between mind and matter, between biology and physics. Others investigate whether DNA repair, enzyme function, or even smell rely on quantum mechanics. Each discovery suggesting life is far stranger than thought, that evolution has been exploiting quantum tricks for billions of years. If nature is secretly using quantum mechanics, what else might be happening inside bodies that has yet to be discovered? Whether quantum coherence plays functional roles in biological processes or is merely an epiphenomenon remains hotly debated. Evidence for quantum effects in photosynthesis and avian magnetoreception exists, but is not universally accepted. Whether biological systems can maintain quantum coherence long enough to provide selective advantage, and through what mechanisms, are questions without consensus. Quantum biology remains an emerging field with ongoing experimental and theoretical work attempting to determine where quantum effects matter and where classical descriptions suffice. Life as currently understood has a strange, unexplained preference. The molecules that constitute DNA, proteins, and even sugars in cells all have a distinct handedness, a concept known as chirality. But here is the mystery. Why does life choose one hand over the other? Chirality means some molecules exist in two mirror image forms, like left and right hands. In theory, both versions should be equally likely to occur in nature, yet life on Earth only uses one type. Amino acids, the building blocks of proteins, are left-handed. Sugars in DNA are right-handed. If chemistry does not favor one over the other, how did this imbalance begin? Scientists have debated this for decades, and several competing theories have emerged. One idea suggests cosmic rays or polarized light from space could have subtly influenced early organic molecules, tipping the scales toward one type of chirality. Another theory proposes an ancient asteroid carrying asymmetric molecules crashed into Earth, seeding life with a built-in preference. Some even argue chirality could be a random accident, a choice life made long ago that simply persisted. But the real controversy: if alien life were found, would its chemistry be identical? Or could an entirely different world be built on opposite-handed molecules, making their biochemistry completely incompatible with terrestrial biology? Consider what this means for the nature of life itself. If chirality is arbitrary, then life elsewhere might be fundamentally incompatible with Earth-based biology, unable to metabolize the same nutrients, unable to interact with the same biochemical pathways. Two forms of life could theoretically coexist on the same planet without ever being able to use each other as food sources. But if chirality is not arbitrary, if some physical principle favors one-handedness over the other, then perhaps all life in the universe shares this same fundamental asymmetry. Perhaps the choice was not random but determined by underlying physics not yet understood. Some researchers investigate whether weak nuclear force, which itself exhibits handedness at the particle level, could have influenced prebiotic chemistry. Others explore whether circularly polarized light from neutron stars could have created chiral imbalances in interstellar organic molecules that eventually seeded planets. Laboratory experiments have attempted to recreate conditions that might generate chiral excess, but results remain inconclusive. Some processes produce slight asymmetries, but amplifying these to the complete homochirality observed in biology remains unexplained. Whether life's handedness is frozen accident, physical necessity, or something between these extremes remains unresolved. How homochirality emerged from presumably racemic prebiotic chemistry is among biology's fundamental mysteries. Whether this represents a universal constraint on life or a contingent historical fact specific to Earth continues to be investigated across origins of life research, astrobiology, and prebiotic chemistry. Imagine a world where electricity flows with zero resistance, no heat, no energy loss, no wasted power. That is the dream of room temperature superconductivity, a phenomenon that could revolutionize technology from power grids to quantum computers. But here is the complication. It might already exist, or it might be total illusion. Superconductors are materials that, under certain conditions, conduct electricity perfectly, but only at extremely low temperatures, often near absolute zero. This makes them impractical for everyday use. Scientists have spent decades searching for a way to make superconductors work at room temperature. And in 2020, a breakthrough was announced, a material that appeared to remain superconducting at 15 degrees Celsius. It was hailed as transformative until skepticism set in. The controversy, reproducibility. Many physicists could not replicate the results, and doubts grew over whether the data had been misinterpreted or, worse, manipulated. Some accused researchers of premature announcement. Others saw the backlash as scientific gatekeeping, resisting new ideas because they challenged established beliefs. But if room temperature superconductivity is real, the implications are enormous. Imagine power grids with zero energy loss, maglev trains that defy friction, or computers that run without overheating. The world's energy problems could be transformed overnight. So are we on the brink of technological revolution? Or is the promise of room temperature superconductivity just another scientific mirage? Consider what makes superconductivity possible at all. At very low temperatures, certain materials allow electrons to pair up and move through the lattice without scattering, without resistance. This is quantum mechanics operating at macroscopic scales, a rare and delicate phenomenon. The question is whether this quantum coherence can be maintained at higher temperatures. Conventional superconductors require temperatures below 30 Kelvin. High-temperature superconductors, discovered in the 1980 seconds, work up to about 130 Kelvin, still far below room temperature and requiring expensive cooling. Claims of room temperature superconductivity typically involve exotic materials under extreme pressures, hundreds of gigapascals, pressures found deep within planetary interiors. Even if such materials superconduct at room temperature, their practical utility is questionable if they require pressure conditions impossible to maintain in applications. Some researchers explore unconventional mechanisms, perhaps superconductivity mediated by something other than phonons, the lattice vibrations that enable conventional superconductivity. Others investigate metastable materials that might be synthesized under extreme conditions but remain superconducting when returned to ambient conditions. Whether room temperature superconductivity at ambient pressure is physically possible, what mechanisms might enable it, and whether reported observations are genuine or experimental artifacts remains highly contested. The field has been marked by both genuine progress and retracted claims. Materials science continues investigating, but definitive room temperature, ambient pressure, superconductivity remains undemonstrated despite decades of effort. What happens when artificial intelligence stops being just a tool and starts thinking like humans? This is the promise and the fear of artificial general intelligence, AGI, a machine capable of reasoning, learning, and adapting just like biological intelligence. Some believe AGI will solve humanity's biggest problems. Others think it could mark extinction. Unlike today's AI, which is designed for specific tasks like recognizing faces, generating text, or driving cars, AGI would be able to think flexibly across multiple domains. It would not just follow instructions, it would create its own solutions, form goals, and possibly even develop self-awareness. But here is the controversy. Can it even happen? Some experts argue intelligence is more than just raw computing power. Conscious thought, creativity, and emotion are deeply tied to biological processes still not fully understood. What if intelligence cannot be replicated in silicon? Others believe it is just a matter of time. Once AI reaches a certain level of complexity, true general intelligence will emerge naturally. Then there is the existential debate. Optimists envision AGI ushering in an era of abundance, solving climate change, curing diseases, making human labor obsolete. But skeptics warn of a runaway intelligence explosion, where AGI rapidly surpasses human capability, making decisions that cannot be predicted or stopped. So will AGI be humanity's greatest invention or biggest mistake? If something as smart as humans or smarter is created, how can it be ensured to remain aligned with human interests? Consider what distinguishes human intelligence. It is not just problem solving, but understanding context, experiencing qualia, possessing intuition developed through embodied existence. Can these be replicated through computation alone, or does intelligence require substrate-specific properties that silicon cannot provide? Some researchers argue AGI is inevitable, that intelligence is substrate independent and can be implemented in any sufficiently complex information processing system. Others contend consciousness and general intelligence are emergent properties of biological neural networks that cannot be duplicated in artificial systems. The alignment problem presents perhaps the greatest challenge, ensuring AGI systems pursue objectives compatible with human values. But human values themselves are diverse, contradictory, and context-dependent. How can values be specified precisely enough to program into superintelligent systems? Some propose creating AGI with limited goals, constrained optimization, or built-in uncertainty about human preferences. Others suggest competitive dynamics between multiple AI systems might provide checks and balances. Still others argue these approaches are insufficient and that AGI development should be halted until alignment is solved. Whether AGI will be achieved, on what time scale, through what methods, and with what consequences remains among the most uncertain and consequential questions in technology. Whether intelligence is fundamentally computational or requires biological substrate, whether consciousness is necessary for general intelligence, and whether alignment is solvable are questions without consensus. Research continues across computer science, neuroscience, and philosophy without definitive conclusions about AGI's feasibility or implications. The universe had a beginning, but does it have an end? That is one of the biggest unanswered questions in cosmology, and depending on interpretation, the fate of everything could range from slow, freezing death to apocalyptic cosmic collapse. The problem, there is no certainty about which scenario will occur. Scientists generally agree the universe is expanding, galaxies rushing away from each other, space itself stretching. But what happens next depends on unseen forces at play. Will expansion continue forever? Will it slow down? Or will it reverse entirely? One theory, called the Big Freeze, suggests expansion will never stop. Over billions, then trillions of years, galaxies will drift so far apart that light itself will not reach between them. Stars will burn out, black holes will evaporate, and the universe will become a dark, empty void, a slow and lonely death. Then there is the opposite idea, the Big Crunch. If gravity proves stronger than expansion, the universe might eventually reverse course, collapsing in on itself until everything is crushed into a single infinitely dense point, just like the Big Bang but in reverse. Some believe this cycle could repeat endlessly, leading to infinite series of rebirths. And then there is the most violent scenario, the Big Rip. If dark energy keeps accelerating expansion, there may come a point where even atoms are torn apart. Space-time itself could unravel, ending everything in a final catastrophic explosion. So will the universe fade away, collapse, or rip itself apart? The answer may determine the ultimate fate of existence and whether anything ever comes after. Consider what each scenario implies about time, causality, and existence itself. In the Big Freeze, entropy reaches maximum, no energy gradients remain to power any processes. Time becomes meaningless when nothing changes. Does time itself end, or does it continue infinitely through a universe where nothing happens? In the Big Crunch, all matter and energy return to a singularity. Does this represent absolute termination, or could quantum effects prevent complete collapse, potentially triggering another expansion? Could information be preserved through such a transition? In the Big Rip, the fabric of space-time itself is torn apart. Not just matter, but the structure of space and time disintegrates. This represents perhaps the most absolute ending, not just the cessation of material existence, but the destruction of the arena in which existence occurs. Current observations suggest the universe is dominated by dark energy and will continue accelerating expansion, favoring the Big Freeze scenario. But uncertainties about dark energy's nature mean other outcomes cannot be excluded. Some cosmologists propose even more exotic scenarios, the universe gradually transitioning to a lower energy vacuum state, bubble nucleation destroying the current space-time structure, or cyclical models where expansion and contraction alternate eternally. Whether the universe has a definite fate, what determines that fate, and whether physical laws themselves might change as the universe evolves, are questions cosmology continues investigating. The ultimate destiny of all matter, energy, space, and time remains uncertain. Observations constrain possibilities but do not yet determine which scenario will actualize over cosmic timescales extending trillions of years into the future. What if the world could be powered with the same energy that fuels the sun? No more fossil fuels, no dangerous radioactive waste, just endless clean energy. That is the promise of nuclear fusion, a technology that has been 30 years away for nearly a century. But is it really possible? Or is it just a futuristic dream that will never be realized? Unlike nuclear fission, which splits atoms apart and produces dangerous waste, fusion works by forcing atoms together just like what happens in the sun's core. Theoretically, it could provide limitless energy using just hydrogen from seawater. But there is a complication. The temperatures needed to make fusion happen are hotter than the center of the sun, over 100 million degrees Celsius. So far, no one has managed to create a fusion reactor that produces more energy than it consumes. The problem is control. Creating a miniature sun on Earth means containing superheated plasma without letting it touch anything, because the moment it does, it vaporizes reactor walls. Scientists have tried using massive magnets, complex lasers, and other techniques, but the breakthrough remains elusive. Some believe fusion is inevitable, a matter of engineering, not physics. Others argue it will always be too expensive and impractical, making solar and wind better bets for clean energy. And then there is the wild card. What if fusion technology becomes so advanced it leads to a new arms race? If nuclear fusion is possible, it could change civilization forever. The question is, will that point ever be reached where it can actually be used, or will it remain an impossible dream? Consider the different approaches being pursued. Magnetic confinement fusion, primarily through tokamak designs, attempts to contain plasma using powerful magnetic fields. This approach has achieved significant milestones but faces engineering challenges in materials that can withstand neutron bombardment and heat loads. Inertial confinement fusion uses powerful lasers to compress fuel pellets, initiating fusion through extreme pressure and temperature. Recent experiments have achieved fusion ignition more energy out than laser energy in, but still far from net positive energy when accounting for total system energy consumption. Alternative concepts include magnetized target fusion, field-reversed configurations, and stellarators. Each approach has theoretical advantages but faces distinct technical hurdles. Even if scientific break-even is achieved, engineering break-even, a reactor producing more usable energy than it consumes, including all auxiliary systems, remains far more challenging. And economic break-even fusion power, competitive with other energy sources, adds another layer of difficulty. Some researchers explore aneutronic fusion reactions that would not produce neutron radiation, potentially simplifying reactor design and reducing activation of structural materials. But these reactions require even higher temperatures and are more difficult to achieve. Whether fusion power will become practical, on what timescale, and whether it can compete economically with renewable energy sources that continue becoming cheaper, remains uncertain. Fusion research continues with substantial public and private investment, but whether it represents humanity's energy future or an expensive scientific pursuit without practical application is unresolved. Right now, an invisible storm of high-energy particles is passing through observation. These particles, known as cosmic rays, come from deep space, traveling at nearly the speed of light. Some of them have more energy than anything humans have ever created, and yet there is no certainty about where they come from. Cosmic rays were first discovered in the early 20th century, when scientists noticed radiation levels increased the higher they went into the atmosphere. But that was just the beginning of the mystery. These particles hit Earth's atmosphere with mind-boggling amounts of energy far beyond what even the most powerful particle accelerators can achieve. Where do they originate? What force in the universe is powerful enough to launch them across galaxies? Some theories suggest supernova explosions. The violent deaths of stars are cosmic ray factories, flinging particles at near-light speeds. Others point to black holes or neutron stars, whose extreme gravitational forces could accelerate particles to unimaginable velocities. And then there is the more exotic idea that cosmic rays might be signatures of entirely new physics, perhaps even evidence of dark matter interactions or relics from the Big Bang itself. What makes this even more perplexing is that some ultra-high energy cosmic rays do not seem to follow any obvious path back to a source. They appear to come from nowhere. This has led to speculation ranging from unknown astrophysical objects to entirely new forces of nature at play. Until this cosmic mystery is unraveled, one thing remains certain. The universe is throwing particles at us with unimaginable energy, and the identity or nature of the thrower is still unknown. Consider the energy scales involved. The most energetic cosmic rays exceed 10-20 electron volts, equivalent to a baseball traveling at 100 kilometers per hour. Except this energy is concentrated in a single subatomic particle. What astrophysical processes can achieve such extraordinary acceleration? The GZK cutoff, a theoretical maximum energy for cosmic rays that have traveled cosmological distances, suggests the highest energy cosmic rays must originate relatively nearby. Yet identifying specific sources has proven difficult. Are they produced in active galactic nuclei, in gamma-ray bursts, in the jets of supermassive black holes? Some cosmic rays are heavy nuclei rather than protons, which constrains acceleration mechanisms. The composition of cosmic rays at different energies provides clues about their sources and the mechanisms that accelerate them. Cosmic rays also play roles beyond astrophysical curiosity. They influence atmospheric chemistry, cloud formation, and potentially even climate. They produce secondary particles that can cause soft errors in electronics and pose radiation hazards for astronauts and high-altitude flight crews. Whether all cosmic rays share common origins, or whether different energy regimes have different sources, what maximum energies are achievable through natural processes, and whether any cosmic rays are extragalactic in origin remain active research questions. Cosmic ray astronomy continues with ground-based detector arrays and space-based instruments, but the origins of the highest energy cosmic rays remain among astrophysics' enduring mysteries. What if the biggest limit on life is not disease, accidents, or habits, but an invisible expiration date written into biology? For centuries, humans have dreamed of extending life indefinitely, but is there a hard ceiling on how long life can last? Right now, the longest verified human lifespan belongs to Jean Calment, who lived to be 122 years old. But is that the upper limit? Or can boundaries be pushed further? Biologists argue aging is a biological program deeply embedded in cells. Over time, DNA damage accumulates, cellular repair slows down, essential systems break down. Some scientists claim that no matter how advanced medicine becomes, human bodies simply cannot sustain life beyond 120 to 150 years. Even with perfect health, cells eventually reach a state where they can no longer divide, known as the Hayflick limit, essentially putting a biological clock on life itself. But not everyone agrees. Longevity researchers believe aging is just another disease, one that can be slowed, stopped, or even reversed. Techniques like gene editing, stem cell rejuvenation, and cellular reprogramming are already showing promise in extending lifespan in animals. Some scientists believe the first person to live to 150 or even 200 has already been born. But if there is no upper limit, what happens if people stop dying? Would society collapse under the weight of immortality? Or is death simply a challenge yet to be conquered? For now, the race to extend human life continues. But whether there is a finish line or a biological wall that can never be broken through remains one of the greatest mysteries of science. Consider the distinction between lifespan and health span. Even if maximal lifespan could be extended, Would additional years be spent in frailty and decline, or could health be maintained throughout? Some longevity interventions appear to compress morbidity, reducing the period of age-related disease rather than simply extending life. Different model organisms show vastly different aging rates and maximum lifespans. Some species exhibit negligible senescence, showing no increase in mortality rate with age. If aging is not universal among complex organisms, is it truly inevitable in humans? Caloric restriction, certain genetic modifications, and pharmaceutical interventions have extended lifespan in laboratory animals. But whether these findings translate to humans and whether extending lifespan in model organisms delays aging or merely postpones death from specific causes remains debated. Evolutionary theories of aging suggest lifespan is not directly selected but is a byproduct of selection for reproductive success early in life. Antagonistic pleiotropy, where genes beneficial early in life become harmful later, and mutation accumulation in late-acting genes could impose limits that cannot be overcome without fundamentally redesigning human genetics. Whether there exists a fixed maximum human lifespan, whether aging is programmed or stochastic, and whether radical life extension is biologically feasible remain unresolved. Research continues across gerontology, genetics, and regenerative medicine, but whether aging is an inevitable feature of complex multicellular life or a potentially solvable problem remains uncertain. Everything around observation, heartbeats, weather, stock markets follows one simple rule: chaos. At first glance, nature seems like a well-ordered system. Planets orbit predictably. Seasons change on time. Life follows patterns of birth and decay. But beneath that order, chaos reigns. The smallest disturbance, a butterfly flapping its wings, a slight shift in ocean currents can set off a chain reaction of unpredictable consequences. This is the essence of chaos theory, the idea that nature is far less stable and predictable than assumptions allow. Weather is the perfect example. Meteorologists use vast amounts of data to predict storms, but beyond a few days, accuracy collapses. That is because even tiny changes in temperature, humidity, or wind speed can send the atmosphere spiraling into unexpected patterns. It is not randomness, it is chaotic determinism. The system follows rules, but those rules are so sensitive that tiny changes lead to vastly different results. Some scientists argue chaos is not just a side effect of nature, it is the driving force behind evolution, climate patterns, and even human behavior. Without chaos, life might never have emerged in the first place. Mutations in DNA, random, chaotic changes, fuel evolution. Unpredictable disasters reshape ecosystems, forcing adaptation. Chaos does not destroy order, it creates it. But not everyone sees it that way. Some physicists believe even the most chaotic systems are just highly complex but ultimately predictable, that if enough information existed, every outcome could be foreseen. Others argue true randomness exists, that some things are inherently unknowable. So does chaos mean nature is fundamentally unpredictable, or are deeper patterns simply being missed, hidden beneath apparent randomness? If the universe itself was born from chaos, does that mean existence in an unpredictable world is assured, or one that only appears that way until learning how to read its patterns? Consider the distinction between deterministic chaos and genuine randomness. Chaotic systems are deterministic, their future states are completely determined by initial conditions and governing equations. Yet they are unpredictable in practice because infinitesimal uncertainties in initial conditions grow exponentially, making long-term prediction impossible regardless of computational power. This sensitivity to initial conditions appears throughout nature: turbulent fluid flow, population dynamics, neural activity, cardiac rhythms. Small perturbations can trigger qualitatively different outcomes, the hallmark of chaos. Strange attractors, geometric structures in phase space toward which chaotic systems evolve, reveal hidden order within chaos. The Lorentz attractor, describing atmospheric convection, has an elegant butterfly-shaped structure despite the system's unpredictable behavior. Some researchers investigate whether quantum mechanics introduces fundamental randomness that breaks deterministic chaos. Others explore whether chaos at macroscopic scales influences quantum systems, potentially bridging classical and quantum physics. In biological systems, chaos may be functional rather than problematic. Chaotic dynamics in neural networks could enhance information processing. Heart rate variability slightly chaotic appears healthier than perfectly regular rhythms. Evolution may have tuned biological systems to operate near the edge of chaos, balancing stability with flexibility. Whether chaos represents incomplete knowledge or fundamental unpredictability, whether it plays constructive roles in natural systems, and how chaos relates to quantum indeterminacy remain subjects of ongoing investigation across physics, mathematics, and biology. The role of nonlinear dynamics in shaping natural phenomena continues to be explored without complete understanding of where chaos is essential versus incidental. What if the brain was working against itself, slowly unraveling everything that makes identity? Neurodegenerative diseases like Alzheimer's, Parkinson's, and ALS are among the most terrifying conditions known to science. They strip away memory, movement, and identity itself. But despite decades of research, there is still incomplete understanding of what causes them. Are they the result of genetics, environmental exposure, a fundamental flaw in how the brain ages? The truth is, pieces of the puzzle are still being assembled, and every answer only seems to bring more questions. For years, scientists believed misfolded proteins were the key culprit. In diseases like Alzheimer's, clumps of beta-amyloid proteins build up in the brain, choking neurons and disrupting communication. In Parkinson's, it is Lewy bodies. In ALS, it is TDP43. But here's the problem. Not everyone with these protein buildups develops the disease. Some people's brains are full of these misfolded proteins, yet they remain cognitively sharp. So if the plaques are not the sole cause, what is? Another theory points to inflammation, the brain's own immune system turning against itself, attacking neurons instead of protecting them. There is also mounting evidence that viruses, gut bacteria, and even exposure to pollutants could be long-term triggers, slowly damaging the brain over decades. And then there is the most unsettling possibility, that neurodegeneration is not caused by one single thing but a combination of genetic predisposition, environmental triggers, and biological processes not yet understood. If the mystery of what truly causes neurodegenerative diseases could be cracked, millions of lives could be changed. But what if the answer is not just one thing but everything at once? Consider the heterogeneity within diagnoses. Alzheimer's disease may represent multiple distinct pathological processes with similar clinical presentations. Genetic studies have identified numerous risk alleles, each contributing small effects, suggesting polygenic architecture. But substantial cases lack identified genetic risk factors, implicating environmental or stochastic components. The protein aggregation hypothesis that misfolded proteins like amyloid beta, tau, alpha-synuclein, or TDP43 drive pathology has dominated research for decades, but clinical trials targeting these proteins have largely failed, raising questions about whether they are causes or consequences of neurodegeneration. Alternative hypotheses propose mitochondrial dysfunction, oxidative stress, impaired protein clearance through autophagy or the ubiquitin proteasome system, neuroinflammation, vascular dysfunction, or prion-like spreading of pathological proteins. Likely, multiple mechanisms interact in complex ways that vary between individuals. The long prodromal phase, decades between initial pathological changes and clinical symptoms, complicates research. By the time diagnosis occurs, substantial irreversible damage has already accumulated. This suggests preventive interventions might need to begin in midlife, but identifying at-risk individuals before symptoms emerge remains challenging. Whether neurodegenerative diseases are inevitable consequences of aging in long-lived species, whether they result from modern environmental exposures, or whether they represent failures of cellular maintenance mechanisms is debated. Why prevalence increases exponentially with age and whether maximum lifespan correlates with neurodegeneration risk across species remain unresolved questions. What causes selective vulnerability, why specific neuronal populations degenerate in different diseases, is incompletely understood. Why motor neurons in ALS, dopaminergic neurons in Parkinson's, or hippocampal neurons in Alzheimer's is poorly explained by current models. Research continues across neuroscience, genetics, and molecular biology, but neurodegeneration's causes remain incompletely characterized. Whether effective therapeutics can be developed without fully understanding etiology is uncertain. Autism is one of the most misunderstood conditions in science. It affects how people think, interact, and perceive the world. But what actually causes it? That question has fueled some of the most heated debates in medicine and neuroscience for decades. The leading theory has been genetics. Studies show autism tends to run in families, and scientists have identified hundreds of genes linked to autistic traits. But here is the problem. No single gene causes autism. Some people with these genes never develop it, while others do without a clear genetic cause. So genetics alone cannot be the whole story. That is where environmental factors come in. Researchers have explored everything from prenatal exposure to toxins, viral infections during pregnancy, complications at birth, and even differences in gut bacteria. Some studies suggest certain chemicals or pollutants might slightly increase risk, while others indicate factors like maternal stress or nutritional deficiencies could play a role. But the tricky part, no single factor has been pinpointed as a definitive cause. And then there is the controversy. For years, misinformation linked vaccines to autism, a claim that has been thoroughly debunked by decades of research. Yet the myth persists, overshadowing real scientific inquiry into the condition. So what is the truth? Right now, the best explanation is that autism is caused by a complex interplay of genetics and environmental influences. Some scientists believe it is not just about risk factors, but about how the brain develops differently in early life. The real challenge is not just understanding autism's causes, it is understanding the diverse ways it manifests. If autism is not one thing but many, how does definition even begin? Consider the spectrum concept. Autism is not a discrete category but encompasses enormous heterogeneity in cognitive abilities, sensory profiles, communication styles, and adaptive functioning. This variability suggests diverse etiologies might converge on similar behavioral phenotypes, or alternatively, that current diagnostic categories group together fundamentally different conditions. Neuroimaging studies reveal differences in brain connectivity, regional volumes, and neural activation patterns in autistic individuals, but findings vary substantially across studies. Whether autism represents fundamentally different neural organization or variation within typical developmental trajectories remains debated. The increase in autism prevalence over recent decades, now estimated at 1 to 2% of children, has sparked debate about whether this represents genuine increase, better recognition, diagnostic substitution, or broadening criteria. Disentangling these factors has proven difficult. Some researchers propose autism represents the extreme of continuous traits present in the general population rather than a discrete disorder. The broader autism phenotype subclinical traits in relatives supports dimensional rather than categorical models. Evolutionary perspectives question why genetic variants associated with autism persist if they reduce reproductive fitness. Possible explanations include balancing selection, where autistic traits confer advantages in certain contexts, or mismatch between ancestral and modern environments. The neurodiversity movement challenges medical model framing, instead conceptualizing autism as neurological difference rather than deficit or disorder. This paradigm shift has implications for research priorities, intervention approaches, and societal accommodation. Whether autism has singular or multiple etiologies, whether it represents disorder or difference, and what interventions are appropriate remain contested. Research continues across genetics, neuroscience, and developmental psychology, but autism's causes and nature remain incompletely understood, reflecting both scientific uncertainty and evolving social conceptualizations of neurological difference.